In the darkness beyond Mars, where sunlight fades to a whisper and Earth becomes nothing more than a pale blue dot, lies a realm that defies every assumption we've ever made about exploration. We think of space travel as humanity's greatest triumph. Rockets thundering skyward, astronauts walking on alien worlds, flags planted in cosmic soil. But what if I told you that everything we've achieved so far, every moon landing, every space station, every Mars rover, has been merely playing in our cosmic backyard? And yet, against all odds, against the very laws of physics themselves, we've somehow managed to send our mechanical ambassadors into this impossible realm, where they've discovered wonders that have rewritten the textbooks of science. How do you journey to a place where the sun's warmth dies, where a radio signal takes hours to whisper home, where the very concept of up and down loses all meaning? Join me as we embark on humanity's most audacious adventure, an impossible journey to the outer solar system, where every mile traveled represents a triumph over the fundamental forces that govern our universe. Before we venture into this cosmic wilderness together, I'd love to know, where in the world are you watching from right now? And what time is it for you? Are you witnessing sunrise over your city? Or are you, like me, gazing up at the night sky? Drop your location and time in the comments below. Let's see how far our own human network spans across this pale blue dot we call home. Imagine standing at the edge of a vast ocean, but instead of water stretching to the horizon, it's an invisible sea of gravitational influence. Earth's final embrace reaching out into the cosmos. This is where our journey to the impossible begins, at the boundary where our planet's grip finally loosens and releases us into the true wilderness of space. Most people think leaving Earth means clearing the atmosphere, maybe reaching the moon. But Earth's influence extends far beyond what you might imagine. Our planet commands a spherical domain called the Hill sphere, a gravitational territory stretching nearly 1 million miles in every direction. Within this realm, Earth is king. Satellites obey its pull, space debris dances to its rhythm, and even our moon remains a faithful companion. But step beyond this invisible boundary, and everything changes. The Hill sphere represents more than just a mathematical concept. It's the edge of our cosmic neighborhood, the place where Earth's protective embrace finally fails. Here, the sun's immense gravity takes command, and any spacecraft venturing further becomes a true wanderer of the solar system, following orbital mechanics that operate on scales our ancestors could never have conceived. Think of it this way: if Earth were a lighthouse on a cosmic shore, the Hill sphere would be the furthest reach of its beam. Beyond that circle of influence, you're navigating by different stars entirely. The familiar rules that govern everything from falling apples to orbiting space stations suddenly give way to the grand celestial mechanics that move planets and comets. This transition isn't gradual, it's surprisingly sharp. One moment, a spacecraft might require only small thruster burns to maintain its position relative to Earth. Cross that invisible line, and suddenly it's caught in the sun's gravitational river, beginning an orbital dance that could last millennia. What makes this boundary so profound is what it represents for human ambition. Every mission we've ever flown to the outer solar system has had to cross this threshold. The moment when our mechanical ambassadors truly leave home and venture into a realm where Earth becomes just another point of light in the cosmic dark. The Hill sphere also explains why missions to the outer planets are so fundamentally different from anything we do in Earth orbit. When the Hubble Space Telescope needs repair, we can send astronauts in a shuttle. When the International Space Station requires supplies, we can launch a cargo ship that arrives in hours. But once a spacecraft crosses Earth's Hill sphere boundary, it's on its own. There are no rescue missions to Jupiter, no supply runs to Saturn. Every component, every backup system, every line of code must be perfect from the moment of departure. Standing at this invisible wall, we begin to grasp the true audacity of outer solar system exploration. We're not just sending machines to distant planets, we're launching them beyond the protective embrace of our home world, into a realm where the very concept of nearby loses all meaning, and where success depends entirely on the brilliance of human engineering and the favorable alignment of cosmic forces we cannot control. Numbers become meaningless. when we talk about the outer solar system. Your mind simply cannot process what 500 million miles actually means. So let me give you a different way to think about the distances we're attempting to conquer. If you could drive a car at highway speed directly to Jupiter, the journey would take you over 600 years. Saturn, more than a millennium. Pluto, when New Horizons visited it, was so distant that the entire span of recorded human civilization wouldn't be enough time to drive there at 65 miles per hour. Holy. But here's where it gets truly mind-bending. Those distances aren't static. The planets are moving, constantly, in their eternal orbital dance around the Sun. By the time a spacecraft reaches Jupiter's position, Jupiter has long since moved on. Mission planners don't aim for where Jupiter is. They aim for where it will be, years in the future. It's like shooting an arrow at a target that won't exist until after the arrow lands. This celestial choreography means that launch windows to the outer planets are rare and precious. Miss your window to Jupiter, and you might wait another 2 years for the next opportunity. Miss your chance at a favorable alignment for a grand tour of multiple worlds, and you might wait human lifetimes for it to occur again. The Voyager missions exploited a planetary alignment that occurs only once every 175 years. The engineers and scientists who planned those missions knew they were seizing a cosmic opportunity that none of them would live to see again. It was literally a once-in-multiple-lifetimes chance to visit all 4 gas giants with economical trajectories. Distance also warps time itself in ways that challenge human intuition. When mission controllers send a command to a spacecraft at Neptune, they wait over 8 hours for confirmation that the message was received. 8 hours. By the time they know their command worked, an entire business day has passed. If something goes wrong, if the spacecraft encounters an emergency, it must diagnose and solve the problem entirely on its own. Earth is simply too far away to help. These distances transform every aspect of spacecraft design and mission planning. Communication systems must be powerful enough to whisper across billions of miles. Power systems must operate reliably for decades without maintenance. Computer systems must be intelligent enough to make life or death decisions autonomously, because waiting for instructions from Earth isn't an option when you're facing an immediate crisis in the depths of space. Seka, nears photobiopispov dev bemins. The tyranny of distance means that outer solar system missions aren't just expensive, they're investments in the future made by people who will likely never see their completion. The engineers who designed Voyager 1 in the 1970s could never have imagined that their creation would still be transmitting data from interstellar space in 2024, long after many of them had passed away. Cross the orbit of Mars, and you enter a fundamentally different universe. The familiar rules that govern missions to the Moon, or even the Red Planet, suddenly become obsolete, replaced by challenges so extreme they seem designed by nature to keep us confined to the inner solar system. The first thing that dies is the sun's warmth. At Earth's distance, our star delivers over 1,300 watts of energy per square meter, enough to power your microwave oven. But energy follows the inverse square law. Double the distance, and you get only 1/4 the power. At Jupiter's distance, that generous solar energy dwindles to just 50 watts per square meter. At Saturn, it's barely 15 watts. By the time you reach Pluto, the sun delivers less energy than a dim light bulb spread across an area the size of a football field. This solar famine kills traditional spacecraft design. The International Space Station's vast solar arrays would be utterly useless at Jupiter, unable to generate enough power to run a laptop computer. Missions to the outer planets must carry their own power sources, typically radioisotope thermoelectric generators, that convert the heat from decaying plutonium into electricity. These nuclear batteries aren't just convenient, they're absolutely essential for survival in the outer darkness. Temperature becomes a constant enemy. Where Earth enjoys a comfortable average temperature suitable for liquid water, the outer solar system is a realm of perpetual winter. Jupiter's cloud tops hover around -145 degrees Celsius, -234 degrees Fahrenheit. Saturn is even colder. At these temperatures, steel becomes brittle as glass. rubber turns to powder, and electronic components behave in ways their designers never anticipated. But perhaps most dramatically, the very nature of planetary science transforms beyond Mars. The inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds with solid surfaces you could theoretically land on. Beyond the asteroid belt, we encounter the realm of the giants, massive worlds made primarily of gas and ice, with no solid surface to explore. This shift fundamentally changes how we design missions. You can't land on Jupiter the way we landed on Mars. There's no there, just layers of increasingly dense atmosphere that would crush any spacecraft long before it reached anything resembling a surface. This tell we. Instead, missions to gas giants become exercises in orbital mechanics and atmospheric diving, brief encounters that must gather years' worth of scientific data in a matter of hours or days. The moons of these giant worlds present their own unique challenges. Europa's surface is constantly bombarded by radiation from Jupiter's magnetic field, levels that would kill a human in minutes and fry electronics in hours. Titan is shrouded in a thick, opaque atmosphere that makes landing like trying to set down in the world's thickest fog. Enceladus spouts geysers of ice particles from its south pole, creating a dynamic, ever-changing environment around Saturn. Communication becomes exponentially more challenging. A radio signal from Mars takes about 20 minutes to reach Earth at its farthest point. From Jupiter, it takes nearly an hour. From the edge of the solar system, over half a day. This means that real-time control of outer solar system missions is impossible. Spacecraft must be programmed with enough intelligence to handle unexpected situations entirely on their own. The outer solar system also reveals phenomena that simply don't exist in the inner planets. Jupiter's radiation belts are so intense they could kill a human in minutes. Saturn's rings create a gravitational environment unlike anywhere else in the solar system. Uranus rotates on its side for reasons we still don't fully understand. Neptune experiences winds faster than the speed of sound, despite receiving almost no energy from the sun. Perhaps most profoundly, the outer solar system is where we encounter the truly alien. While Mars might one day host human colonies, and Venus might be terraformed by future generations, the outer planets represent environments so extreme, so utterly hostile to human life, that they will likely remain forever accessible only to our mechanical ambassadors. This is the realm where our spacecraft become humanity's sensory organs, extending our ability to see, feel, and understand into regions where human bodies could never survive. Beyond Mars, exploration becomes a purely technological endeavor, dependent entirely on the ingenuity of our engineering and the robustness of our automated systems. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky wrote down an equation that would forever define the boundaries of human ambition in space. It's elegant in its simplicity, devastating in its implications, and the reason why missions to the outer solar system seem to violate the very laws of physics. The rocket equation, also known as the Tsiolkovsky equation, tells us exactly how much energy we need to go anywhere in space. And when you plug in the numbers for a journey to Jupiter, Saturn, or beyond, the results are so absurd, they seem like a cosmic joke played by the universe itself. Here's the cruel mathematics. To accelerate a spacecraft, you need fuel, but fuel has mass, and that mass must also be accelerated, requiring even more fuel. That additional fuel also has mass, requiring still more fuel to accelerate it. The equation spirals into an exponential nightmare, where the fuel requirements grow faster than your ability to carry fuel. Consider this mind-bending reality. If you wanted to send a small car to Jupiter using conventional chemical rockets, you would need a fuel tank the size of several city blocks. Want to send something heavier, like a space station module, you'd need more fuel than exists in all the gas stations on Earth. And that's just to Jupiter, the closest of the gas giants. The numbers become even more surreal when you consider return trips. A mission to Jupiter and back would require fuel masses measured in millions of tons. far more than the entire mass of every rocket ever built in human history combined. This is why no human has ever traveled beyond the moon, and why most scientists believed missions to the outer planets would remain forever impossible. But Tsiolkovsky's equation doesn't just govern fuel, it governs hope itself. When NASA scientists first calculated trajectories to the outer planets in the 1960s, the fuel requirements were so astronomical that many concluded such missions were purely theoretical exercises. The rockets needed would be larger than skyscrapers, the costs greater than national budgets, the technical challenges beyond human capability. The equation seemed to impose a fundamental limit on human exploration, a mathematical prison that confined us to the inner solar system. Launch a spacecraft with enough fuel to reach Saturn, and the rocket would collapse under its own weight on the launch pad. Try to build a bigger rocket, and you need even more fuel, making the problem exponentially worse rather than better. This is where the true genius of space exploration reveals itself. Unable to defeat the rocket equation through brute force, engineers had to become cosmic magicians, finding ways to cheat physics itself. They realized that the equation assumes you're fighting gravity and distance entirely with your own energy. But what if you could steal energy from other sources? The breakthrough came from understanding orbital mechanics, not as obstacles to overcome, but as tools to exploit. Every planet in the solar system is essentially a massive energy reservoir, storing tremendous kinetic and gravitational potential energy in its orbital motion around the Sun. The question wasn't how to carry enough fuel to reach the outer planets. It was how to tap into this existing energy. This realization led to the development of gravitational assist maneuvers, where spacecraft could steal orbital energy from planets themselves. Instead of fighting the rocket equation head-on, missions could use the planets as gravitational slingshots, gaining velocity and changing direction without burning a single drop of fuel. But even gravitational assists couldn't completely solve the equation's cruel logic. They could help, but they couldn't work miracles. The fundamental challenge remained: how do you design a spacecraft light enough to be launched by available rockets, yet robust enough to survive decades in the harshest environment imaginable? The answer required a complete reimagining of spacecraft design philosophy. Instead of building heavy, robust machines like military aircraft, outer solar system missions demanded spacecraft that were gossamer light yet incredibly resilient. Every component had to justify its existence in terms of both mass and mission-critical function. Every gram was precious, every system redundantly backed up, every design decision scrutinized through the lens of Tsiolkovsky's unforgiving mathematics. The Voyager spacecraft exemplify this philosophy. Each weighs only 825 kilograms, less than a small car, yet carries instruments sensitive enough to detect magnetic fields, cameras capable of revealing moons around distant planets, and communication systems powerful enough to whisper across billions of miles. They represent the absolute pinnacle of engineering efficiency, where every bolt, wire, and circuit board has been optimized to extract maximum scientific return from minimum mass. Even today, despite decades of technological advancement, the rocket equation continues to govern our ambitions. The reason we don't have regular flights to Jupiter isn't lack of interest or funding, it's pure mathematics. Until we develop fundamentally new forms of propulsion, perhaps fusion rockets or solar sails, the outer solar system will remain accessible only to our most carefully crafted mechanical ambassadors. The rocket equation teaches us a profound lesson about the nature of exploration itself. Sometimes the greatest victories come not from overwhelming force, but from accepting limitations and finding creative ways to work within them. The outer solar system missions represent humanity at its most ingenious, not conquering the cosmos through brute strength, but dancing with the fundamental forces of physics to achieve the seemingly impossible. In the end, Tsiolkovsky's equation didn't stop us from reaching the outer planets. It forced us to become smarter, more creative, and more resourceful than we ever thought possible. Every spacecraft now traveling in the depths of the solar system is a testament to human ingenuity triumphing over mathematical inevitability. Beyond the rocket equation's mathematical barriers lies an even more insidious enemy: The fundamental laws of physics themselves seem designed to prevent exploration of the outer solar system. Every mile you travel away from Earth and the Sun stacks another challenge onto the growing pile of obstacles that would make any reasonable engineer simply give up. Start with power, the lifeblood of any spacecraft. Solar panels, the workhorses of near-Earth missions, become increasingly useless as you venture outward. The solar energy available at Jupiter is only 4% of what Earth receives. At Saturn, it drops to barely 1%. By the time you reach Uranus, solar panels generate so little power, they're essentially decorative. This isn't a gradual decline, it's a cliff drop that forces a complete redesign of how spacecraft generate and manage energy. Traditional batteries can't bridge this gap. The missions we're discussing last decades, far beyond the lifespan of any chemical battery ever created. This power crisis forced engineers to embrace nuclear technology, specifically radioisotope thermoelectric generators, RTGs, that convert the heat from decaying plutonium into electricity. But RTGs present their own challenges. They're expensive, controversial, and produce only modest amounts of power that steadily decline over time. Temperature presents another exponential challenge. Electronic components designed to operate at Earth normal temperatures begin failing in the extreme cold of the outer solar system. Computer processors slow down, memory chips lose data, mechanical systems freeze solid, materials that are flexible at room temperature become brittle as glass at -200 degrees Celsius. Lubricants turn to solid blocks, seals crack, and metal components contract at different rates, creating stresses that can tear spacecraft apart from the inside. The communication challenge multiplies these difficulties. Radio signals follow the same inverse square law as solar energy, double the distance, and you receive only 1/4 the signal strength. A spacecraft at Jupiter must transmit with 25 times more power than one at Earth's distance, just to deliver the same signal strength to our receivers. At Neptune, that multiplier becomes nearly 900. But signal strength is only part of the problem. The speed of light, normally considered instantaneous for human purposes, becomes a significant delay over interplanetary distances. Commands sent to Voyager 1, now in interstellar space, take over 22 hours to arrive. If the spacecraft encounters an emergency, it must diagnose and solve the problem entirely on its own before Earth even knows there's a crisis. Radiation adds another layer of complexity. Jupiter's magnetic field traps high-energy particles in radiation belts, so intense they would kill an unprotected human in minutes. These particles don't just threaten biological tissue, they gradually degrade electronic components, flip bits in computer memory, and can cause sudden catastrophic failures in sensitive instruments. Spacecraft visiting Jupiter must be hardened against radiation levels that dwarf anything encountered in Earth orbit. The outer solar system also presents navigational challenges that strain human understanding. At interplanetary distances, the gravitational influences of all the planets, moons, asteroids, and even the pressure of solar radiation become significant factors in spacecraft trajectory. Mission planners must account for gravitational perturbations from objects billions of miles away, solar wind pressure that can gradually alter a spacecraft's path, and relativistic effects that become noticeable over the decades-long durations of these missions. Perhaps most insidiously, time itself becomes an enemy. Components that work perfectly during ground testing may fail after years of exposure to cosmic radiation, thermal cycling, and mechanical stress. Software bugs that were undetectable during Earth-based testing can manifest after years of operation, when the spacecraft is too far away for real-time troubleshooting. Mission planners must anticipate failures that won't occur for decades and design workarounds for problems they can't yet imagine. The outer solar system doesn't just challenge our technology, it challenges our entire approach to engineering. Spacecraft designed for Earth orbit can be repaired, upgraded, or replaced if they fail. But once a probe passes beyond Mars, it must function flawlessly for its entire mission duration, potentially decades, with no possibility of maintenance or repair. This harsh reality forced the development of entirely new engineering philosophies. Outer solar system spacecraft must be built with multiple layers of redundancy, where critical systems have backup systems, and backup systems have 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 backup systems and backup systems have backup systems and backup systems have backup systems have backup systems and backup systems have backup systems have backup systems have backup systems have back. They must be designed to operate autonomously, making complex decisions without human intervention. They must be robust enough to survive environments that would destroy most human-made objects, yet sensitive enough to detect phenomena that barely register above the noise floor of their instruments. The physics of the outer solar system doesn't just make exploration difficult, it makes every successful mission a minor miracle of engineering persistence and human ingenuity. Every image from Jupiter, every measurement from Saturn, every data point from the edge of the solar system represents a victory over the fundamental forces that govern our universe. In 1983, something impossible happened. Pioneer 10, humanity's first spacecraft to visit Jupiter and venture into the outer solar system, began slowing down, not by much, just a tiny fraction of a meter per second squared, barely detectable above the noise of measurement errors. But in the precise world of celestial mechanics, where every force is accounted for and every trajectory predicted years in advance, even tiny deviations are profound mysteries. The Pioneer anomaly, as it came to be known, represented everything strange and wonderful about exploring the outer solar system. Here was a spacecraft that had performed flawlessly for over a decade, sending back humanity's first close-up images of Jupiter and proving that missions to the gas giants were possible. Yet it was behaving in a way that violated our understanding of physics itself. Mission controllers initially assumed it was a simple measurement error. Deep space navigation requires tracking spacecraft positions to extraordinary precision, errors of a few kilometers after traveling billions of miles. But as months turned to years, the anomaly persisted. Pioneer 10 was consistently, measurably slowing down by forces that shouldn't exist. The effect was tiny, about 10 billion times weaker than Earth's gravity, but it was real, consistent, and completely unexplained. Pioneer 11, launched on a similar trajectory, showed the same mysterious deceleration. Two independent spacecraft, identical designs, both experiencing the same impossible phenomenon. Scientists proposed dozens of explanations, each more exotic than the last. Perhaps it was dark matter, the mysterious substance that supposedly fills the universe but interacts only weakly with normal matter. Maybe it was a previously unknown force that only manifests at enormous distances from gravitational sources. Some suggested modifications to Einstein's theory of general relativity, or new physics that emerged only at the scale of the solar system. The anomaly sparked a cottage industry of theoretical papers and heated scientific debates. If the Pioneer spacecraft were experiencing unknown forces, what did that mean for our understanding of gravity, space-time, and the fundamental structure of the universe? Were we witnessing the first evidence of physics beyond the standard model, discovered not in billion-dollar particle accelerators, but in the trajectories of aging spacecraft? For nearly 3 decades, the Pioneer anomaly remained one of the great unsolved mysteries of space exploration. It represented the humbling reality that even our most successful missions could reveal phenomena that challenged our most basic assumptions about how the universe works. The resolution, when it finally came, was simultaneously disappointing and beautiful. In 2012, a team of researchers conducted an exhaustive analysis of every possible source of force acting on the Pioneer spacecraft. They discovered that the anomaly could be entirely explained by thermal radiation, heat radiating from the spacecraft's radioisotope, thermoelectric generators, and electronic components. The RTGs that powered Pioneer generated heat as a byproduct of radioactive decay. This heat radiated asymmetrically from the spacecraft, creating a tiny but persistent thrust that gradually slowed the probe's motion. It wasn't new physics or exotic dark matter. It was simple thermodynamics, operating at levels so subtle that it took decades of careful analysis to detect and measure. Yet the pioneer anomaly's mundane explanation doesn't diminish its significance. It perfectly illustrates how the outer solar system challenges our understanding in unexpected ways. The extreme distances, long mission durations, and precise measurements required for deep space navigation create conditions where even tiny, overlooked effects become visible and important. The anomaly also demonstrates the incredible precision of modern space navigation. We can track spacecraft positions to within meters after they've traveled billions of miles and operated for decades. We can detect accelerations so small they would be completely unnoticeable in everyday life, yet significant enough to require explanation in the context of orbital mechanics. Most importantly, the pioneer anomaly reminds us that exploration of the outer solar system continues to surprise us. Every mission ventures into realms where human experience provides no guide and where our theories are tested under conditions impossible to replicate on Earth. Sometimes the surprises revolutionize physics. Sometimes they simply remind us that even the most mundane physical processes can create profound mysteries when they operate at the scale of the cosmos. The outer solar system remains a place where the impossible happens regularly, where our best theories encounter their limits, and where every successful mission is both a triumph of engineering and a step into the unknown. Imagine the solar system as the universe's most elegant billiard table, where planets roll through space in perfect, predictable paths, each carrying tremendous momentum that can be borrowed, redirected, and amplified by any clever spacecraft that knows how to ask politely. This is the conceptual revolution that transformed impossible missions into achievable dreams. The realization that gravity isn't just an obstacle to overcome, but a resource to exploit. For the first decade of the space age, engineers thought about interplanetary travel the same way they thought about terrestrial transportation. Point your vehicle toward your destination and apply thrust until you arrive. This brute force approach worked fine for reaching the moon, a mere 3-day journey with straightforward physics. But apply this thinking to Jupiter or Saturn, and the fuel requirements become absurd, the mission costs astronomical, and the technical challenges insurmountable. The breakthrough came from a fundamental shift in perspective. Instead of viewing space as empty void that spacecraft must cross, using their own energy, visionary engineers began to see it as an ocean of gravitational currents that could be navigated, exploited, and ridden like a cosmic highway system. Every planet in the solar system is essentially a massive flywheel, storing enormous amounts of kinetic energy in its orbital motion around the Sun. Jupiter, for instance, carries more orbital energy than all other planets combined, a tremendous reservoir of momentum just waiting to be tapped by any spacecraft, clever enough to approach at the right angle, at the right time, with the right trajectory. The physics of gravitational assists, or slingshot maneuvers, are beautifully elegant. A spacecraft approaching a planet from behind, relative to the planet's orbital motion, can steal a tiny fraction of the planet's momentum, gaining speed and energy in the process. The planet loses an infinitesimally small amount of orbital energy, so small it's essentially unmeasurable, while the spacecraft gains a tremendous velocity boost that would require enormous amounts of fuel to achieve through conventional propulsion. Think of it like catching a ride on a moving train. You run alongside the train and grab onto a handle as it passes. Suddenly, you're moving at the train's speed without having to accelerate yourself. The train barely notices your added mass, but you've gained tremendous momentum essentially for free. Gravitational assists work on the same principle, but with spacecraft catching rides on planets moving at tens of thousands of miles per hour. But gravitational assists are far more sophisticated than simple speed boosts. They can redirect a spacecraft's path, sending it toward destinations that would be completely unreachable with onboard propulsion alone. They can provide multiple velocity changes during a single planetary encounter, allowing spacecraft to visit several moons of a planet in rapid succession. Most remarkably, They can send spacecraft to destinations that require negative energy, places you can only reach by first gaining speed, then shedding it through additional gravitational encounters. The mathematics of gravitational assists are fiendishly complex, requiring precise calculations of planetary positions, orbital mechanics, and spacecraft trajectories years into the future. Mission planners must predict exactly where each planet will be, not just at the moment of encounter, but at the precise instant when the spacecraft arrives, after traveling for months or years through space. They must account for the gravitational influences of all the planets, the pressure of solar radiation, and even relativistic effects that become significant over interplanetary distances. More challenging still, these cosmic billiard shots must be lined up in sequence. A spacecraft using Jupiter's gravity to reach Saturn must arrive at Jupiter at exactly the right time, from exactly the right direction, with exactly the right velocity to set up the subsequent encounter. Miss any of these parameters by even small amounts, and the entire mission fails. The elegance of gravitational assists extends beyond their mathematical beauty. They represent a profound philosophical shift in how humans approach seemingly impossible challenges. Instead of overwhelming obstacles with brute force, gravitational assists succeed through patience, precision, and deep understanding of natural systems. They work with the universe's existing energy flows, rather than fighting against them. This approach has enabled missions that would otherwise be completely impossible. Voyager 2's grand tour of all 4 gas giants required gravitational assists from each planet to reach the next. Without Jupiter's gravity boost, the spacecraft could never have reached Saturn. Without Saturn's assistance, Uranus would have remained unreachable. The entire outer solar system exploration program exists only because engineers learned to see gravity as an ally rather than an enemy. Perhaps most remarkably, gravitational assists can actually improve mission reliability and scientific return. By reducing the need for large fuel reserves and powerful engines, they allow spacecraft to carry more scientific instruments and operate for longer periods. The energy that might have been spent on propulsion can instead power cameras, spectrometers, and magnetometers that reveal the secrets of distant worlds. Gravitational assists transformed the solar system from an impossible frontier into a navigable ocean, where skilled mission planners could chart courses to the most distant worlds using nothing more than precise timing, careful mathematics, and the borrowed momentum of planets themselves. In 1965, a young aerospace engineer named Gary Flandreau was working on trajectory calculations at NASA's Jet Propulsion Laboratory when he stumbled upon a cosmic coincidence so rare and extraordinary that it occurs only once every 175 years. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were slowly aligning themselves in a configuration that would make a grand tour of all 4 worlds possible with 1970s technology. Flandreau had discovered the ultimate gravitational highway, a celestial arrangement that would define humanity's exploration of the outer solar system for decades to come. The alignment wasn't perfect. Planets never line up in a straight row like pearls on a string, but they were positioned such that a spacecraft launched at precisely the right moment could visit each world in succession, using the gravity of each planet to accelerate toward the next. Without this alignment, visiting all 4 gas giants would require separate missions, multiple decades, and costs that would dwarf the Apollo program. The window for this cosmic opportunity was heartbreakingly narrow. Launch too early, and the planets wouldn't be in the right positions for the gravitational assists to work. Launch too late, and the alignment would begin to degrade, making the outer planets increasingly difficult to reach. A window for this cosmic opportunity, this cosmic session de Calve and Seth in near. The launch window opened in 1977 and would remain favorable for only a few short years. NASA initially envisioned an ambitious grand tour program with 4 spacecraft. 2 would visit Jupiter, Saturn, and Pluto, while 2 others would explore Jupiter, Uranus, and Neptune. These missions would carry advanced nuclear power sources, sophisticated scientific instruments, and enough fuel for extended orbital operations around each target planet. The estimated cost was staggering, even by space program standards, and Congress balked at funding such an expensive endeavor during a period of economic uncertainty. The program was cancelled, but Flandreau's discovery was too valuable to abandon. NASA's engineers proposed a scaled-back alternative, two smaller, simpler spacecraft that would visit Jupiter and Saturn with the possibility of extended missions if the hardware survived long enough. These missions were designated Voyager, and they would become the most successful planetary exploration program in history. The Voyager spacecraft were marvels of engineering efficiency. Each weighed only 825 kilograms, less than a small car, yet carried 11 different scientific instruments capable of studying magnetic fields, plasma particles, cosmic rays, and planetary atmospheres. Most importantly, each carried sophisticated cameras that could transmit high-resolution images across billions of miles of space, bringing the outer planets into human view for the first time. The launch sequence was carefully choreographed to maximize the gravitational assist opportunities. Voyager 2 launched first on August 20th, 1977, followed by Voyager 1 on September 5th. Despite launching later, Voyager 1 followed a faster trajectory that would arrive at Jupiter first, serving as a pathfinder for its twin and providing backup coverage of the most critical scientific objectives. The Jupiter encounters in 1979 exceeded all expectations. Both spacecraft revealed the giant planet's complex atmospheric dynamics, discovered active volcanoes on Io, and found evidence of a subsurface ocean beneath Europa's icy crust. But perhaps most importantly, the gravitational assists worked perfectly, accelerating both spacecraft towards Saturn with enough velocity to complete their primary missions. At Saturn, the mission plan called for difficult choices. Voyager 1 would make a close approach to Titan, Saturn's largest moon, but this encounter would bend its trajectory northward, out of the plane of the solar system, ending any possibility of continuing to Uranus and Neptune. Voyager 2 would sacrifice the close Titan flyby to maintain the trajectory needed for the extended mission to the ice giants. The Titan decision proved scientifically valuable, but bittersweet. Voyager 1 discovered that Titan possessed a thick atmosphere and complex chemistry that might resemble early Earth, but the spacecraft's cameras couldn't penetrate the haze to reveal the surface. The close encounter provided crucial data about Titan's atmosphere, but left many questions unanswered, questions that wouldn't be resolved until the Cassini-Huygens mission arrived at Saturn decades later. Meanwhile, Voyager 2 continued toward Uranus, entering truly uncharted territory. No spacecraft had ever traveled so far from the Sun, and mission controllers weren't even certain their communication systems would work across such enormous distances. The spacecraft was now so far from Earth that radio signals took over 2.5 hours to make the round trip, making real-time control impossible. The Uranus encounter in January 1986 revealed a world unlike anything in our solar system. The planet rotates on its side, likely due to an ancient collision, and possesses a tilted magnetic field that defied theoretical predictions. Voyager 2 discovered 10 new moons and confirmed that Uranus possesses faint rings, making it the second ringed planet known at the time. The final gravitational assist at Uranus sent Voyager 2 toward Neptune, the outermost of the gas giants and the last major unexplored world in our solar system. By the time the spacecraft reached Neptune in August 1989, it had been traveling for nearly 12 years, operating far beyond its design specifications, in conditions more extreme than its builders had ever imagined. Neptune's encounter provided a grand finale worthy of the Grand Tour concept. The spacecraft discovered that Neptune, despite receiving almost no energy from the Sun, possesses the most dynamic atmosphere in the solar system, with winds exceeding 1,500 miles per hour. It found 6 new moons, including Triton, a captured Kuiper Belt object with active geysers erupting from its south polar region. With Neptune behind them, both Voyager spacecraft began their ultimate journey into interstellar space, carrying humanity's first messages to the stars in the form of the Golden Records. They had accomplished everything originally envisioned for the Grand Tour program, at a fraction of the cost, and with far greater scientific return than anyone had dared to hope. The Voyager Grand Tour represents more than just a successful space mission. It embodies humanity's ability to recognize rare opportunities and seize them with boldness and precision. Flandreau's discovery of the planetary alignment created a narrow window of cosmic possibility, and NASA's engineers and scientists had the vision, skill, and determination to exploit that opportunity fully. Today, both Voyager spacecraft continue their journey into the interstellar medium, still transmitting data about the boundary between our solar system and the galaxy beyond. They remain humanity's most distant ambassadors, carrying the story of a species that learned to read the gravitational currents of space and ride them to the very edge of the known universe. Gravitational assists aren't just about stealing energy from planets, they're about choreographing a cosmic dance so intricate and precise that it would make the world's greatest ballet companies weep with envy. Each planetary encounter requires spacecraft to arrive at exactly the right place, at exactly the right time, with exactly the right velocity, while the target planet itself is hurtling through space at tens of thousands of miles per hour. Consider the complexity of a single Jupiter flyby. The spacecraft approaches from millions of miles away, hollowing a trajectory calculated years in advance. Jupiter itself is a moving target, orbiting the Sun at nearly 30,000 miles per hour, while rotating on its axis every 10 hours. The spacecraft must thread the needle between Jupiter's deadly radiation belts and its extensive moon system, all while positioning itself to steal exactly the right amount of orbital energy to reach its next destination. But the true artistry emerges when missions attempt multiple gravitational assists in sequence. The Cassini mission, for example, used a mind-bending sequence of flybys, Venus twice, Earth once, and Jupiter once, before finally arriving at Saturn 7 years after launch. Each encounter had to be precisely timed and positioned to set up the next, like a cosmic Rube Goldberg machine, where every element must work perfectly or the entire sequence fails. The mathematics involved are staggering in their complexity. Mission planners must solve what's essentially a multi-body gravitational problem, accounting for the positions and motions of all the planets, their moons, and even large asteroids that might perturb the spacecraft's trajectory over years of flight time. 4. They must factor in the pressure of solar radiation, which becomes significant over interplanetary distances, and even relativistic effects that emerge during high-speed planetary encounters. More remarkably, these cosmic dances often involve timing constraints measured in minutes or even seconds. Arrive at Jupiter just a few hours late, and the subsequent Saturn encounter might be off by thousands of miles, potentially sending the spacecraft past the planet entirely instead of into the desired orbit. The precision required is equivalent to shooting an arrow from New York and hitting a moving target the size of a dinner plate in Los Angeles. Some gravitational assist maneuvers push the boundaries of what seems physically possible. The Parker Solar Probe, designed to study the Sun's corona, uses repeated Venus flybys to gradually lower its solar approach distance. Each Venus encounter strips away a small amount of the spacecraft's orbital energy, allowing it to fall deeper into the Sun's gravitational well. It's like using planetary billiards to thread a needle while falling toward a blast furnace. The Juno mission to Jupiter demonstrated another exotic gravitational dance. To study Jupiter's interior structure, the spacecraft needed to enter a highly elliptical polar orbit, a trajectory that's naturally unstable due to gravitational perturbations from Jupiter's moons. Mission planners designed a complex sequence of orbital adjustments and gravitational assists from the moons themselves to maintain Juno's scientific orbit while preventing it from crashing into Jupiter or being ejected from the system entirely. The SUDI. Perhaps most elegantly, modern missions have learned to perform gravitational assists using planetary moons rather than the planets themselves. These moon-assisted maneuvers allow fine-tuning of trajectories and can provide multiple small velocity changes during extended orbital tours. The Cassini mission used dozens of flybys of Titan to reshape its orbit around Saturn, essentially using the large moon as a gravitational tugboat to visit other moons and regions of the Saturn system. The precision of these gravitational dances has improved to the point where mission planners can now design resonant trajectories that use planetary gravity to maintain specific orbital relationships over extended periods. Some missions enter what's called gravitational resonance with planetary moons, where the spacecraft's orbital period matches some fraction of the moon's period, allowing repeated close encounters for intensive study. These gravitational choreographies represent humanity at its most ingenious, using nothing but precise mathematics, careful timing, and deep understanding of celestial mechanics to achieve seemingly impossible feats of exploration. Every successful gravitational assist is a testament to our species' ability to find elegant solutions to complex problems, turning the vast scale and immense forces of the solar system into tools for discovery. The outer solar system missions have elevated gravitational assists from simple engineering techniques into high art, where spacecraft dance through space with a grace and precision that would be beautiful even if they weren't revolutionizing our understanding of the cosmos. These cosmic ballets continue to unfold across the solar system, carrying our mechanical ambassadors to worlds that remain forever beyond human reach. There's a spacecraft right now, this very second, farther from Earth than any human-made object has ever traveled. Voyager 1 is racing through interstellar space at 38,000 miles per hour, still transmitting data after more than 4 decades of operation. Its computers are less powerful than a modern calculator, its memory capacity smaller than a digital photo, yet it continues to function flawlessly in an environment that would destroy most human technology in seconds. This is the profound paradox of outer solar system exploration. To reach the most extreme environments in our cosmic neighborhood, we must build machines that are simultaneously more robust and more delicate than anything we create for use on Earth. They must withstand decades of cosmic radiation, temperature swings of hundreds of degrees, and the mechanical stresses of launch and interplanetary travel, yet remain sensitive enough to detect magnetic fields weaker than Earth's own magnetic influence, and photograph objects billions of miles away. The engineering philosophy for outer solar system missions is fundamentally different from anything else humans build. On Earth, we design cars to last maybe 20 years, buildings to stand for a century, and even our most durable infrastructure rarely needs to function for more than human lifetimes. But spacecraft, destined for the outer planets, must operate reliably for decades without any possibility of maintenance, repair, or replacement. This drives every design decision toward obsessive redundancy and fault tolerance. Critical systems have backup systems, and those backup systems have their own backups. Voyager's computers, for example, each contain 3 identical processing units that vote on every calculation. If one unit disagrees with the other 2, it's automatically ignored. The spacecraft's attitude control system includes multiple gyroscopes, star trackers, and sun sensors, any combination of which can maintain proper orientation if others fail. But redundancy alone isn't enough when you're planning missions that may last decades. Components must be selected not just for their performance, but for their long-term stability and resistance to degradation. Electronic parts that would work perfectly in Earth applications might fail after years of exposure to cosmic radiation. Materials that seem robust in terrestrial testing might become brittle in the extreme cold of the outer solar system. The selection process for space-qualified components is exhaustive and expensive. Engineers subject every part to thermal cycling, vibration testing, radiation exposure, and accelerated aging protocols that simulate decades of operation in space. Parts that pass these tests are then subjected to even more stringent analysis, including X-ray inspection to detect microscopic flaws, and extensive documentation to track every aspect of their manufacturing history. This obsessive attention to component reliability means that outer solar system spacecraft often use technology that seems primitive by contemporary standards. Voyager's computers, built in the 1970s, use magnetic tape for data storage and process information at speeds measured in thousands of operations per second, rather than the billions that modern processors achieve. But this primitive technology was chosen specifically for its proven reliability and resistance to the harsh environment of deep space. The physical construction of these spacecraft reflects their extreme operational requirements. Structures must be lightweight enough to launch yet strong enough to survive the violent acceleration of rocket launch, the thermal shock of leaving Earth's atmosphere, and the mechanical stresses of decades in space. Materials are chosen not just for strength and weight, but for their behavior across extreme temperature ranges and their resistance to micrometeorite impacts. Perhaps most remarkably, outer solar system spacecraft must be designed to adapt and evolve during their missions. Software systems must be reprogrammable from billions of miles away, allowing mission controllers to upload new instructions, modify operational procedures, and even reprogram fundamental spacecraft behaviors as mission requirements change or unexpected situations arise. The New Horizons spacecraft exemplifies this adaptive capability. Originally designed for a flyby of Pluto, the mission was extended to visit the Kuiper Belt object Arrokoth after the primary mission's success. This required completely reprogramming the spacecraft's attitude control systems, navigation software, and scientific observation sequences, while the probe was traveling through the outer solar system with communication delays of over 4 hours each way. Thermal management presents unique challenges for outer solar system missions. Spacecraft must maintain their electronic systems within operational temperature ranges, while external temperatures plunge to hundreds of degrees below freezing. This requires sophisticated thermal control systems that use radioactive decay, heat, electrical heaters, and carefully designed insulation to maintain livable conditions for sensitive components. The integration of all these systems, power, communication, navigation, scientific instruments, and thermal control, must be orchestrated with precision that borders on the miraculous. Every system affects every other system, and the failure of any single component can potentially end a billion-dollar mission. The engineering challenge isn't just building individual systems that work, but ensuring they work together harmoniously for decades in an environment where repair is impossible and failure is catastrophic. These spacecraft represent humanity's most durable creations, designed not just to survive, but to thrive in conditions more extreme than anything on Earth. They are, in the truest sense, built for eternity, mechanical immortals carrying our curiosity and ambition into the cosmic dark, continuing to function and discover long after their builders have passed into history. 400 million miles from the Sun, solar panels become expensive decorations. At Jupiter's distance, our star provides barely 4% of the energy it delivers to Earth, not enough to power a household light bulb per square meter of solar panel. Venture to Saturn, and that meager trickle drops to just 1%. By the time you reach the edge of the solar system, solar energy becomes so faint it's essentially non-existent. This solar energy cliff creates the single greatest engineering challenge for outer solar system exploration. How do you power sophisticated scientific instruments, communication systems, and spacecraft operations when your most reliable energy source, the Sun itself, abandons you in the cosmic dark? The solution required embracing technology that most space agencies had avoided: nuclear power, specifically radioisotope thermoelectric generators, or RTGs, devices that convert the heat from radioactive decay directly into electricity. These nuclear batteries don't involve fission reactions or chain reactions like nuclear power plants. Instead, they rely on the steady, predictable decay of plutonium-238, which generates heat continuously for decades. RTGs sound like science fiction, but they're elegantly simple devices. Pellets of plutonium dioxide are surrounded by thermocouples, devices that generate electricity when one side is hot and the other is cold. The radioactive decay keeps one side warm, while the cold vacuum of space chills the other side, creating a temperature difference that produces electrical current. No moving parts, no chemical reactions, just the fundamental physics of thermoelectric conversion powered by atomic decay. The beauty of RTGs lies in their reliability. Unlike solar panels, which can be damaged by micrometeorites, covered by dust, or degraded by radiation, RTGs are essentially indestructible. They produce power steadily, regardless of spacecraft orientation, distance from the Sun, or local environmental conditions. They're the ultimate set-it-and-forget-it power source, perfect for missions that must operate autonomously for decades. But RTGs come with significant challenges. Plutonium-238 is one of the most expensive materials on Earth, costing more per gram than the finest diamonds. The United States stopped producing it in 1988, creating a supply crisis that threatened to end outer solar system exploration entirely. NASA had to carefully ration its existing plutonium stockpile while working with the Department of Energy to restart production, a process that took over 2 decades and billions of dollars. The power output of RTGs is also modest and continuously declining. Voyager's RTGs originally produced about 470 watts of electricity, enough to power a few household appliances. After 4 decades of operation, they now generate less than 250 watts, barely enough to run the spacecraft's most essential systems. Mission planners must design power budgets that account for this steady decline, gradually shutting down non-critical systems as available power diminishes. This power limitation forces ruthless prioritization of spacecraft systems and scientific instruments. Every watt must be justified in terms of mission-critical function. Heating systems compete with communication systems, which compete with scientific instruments, all for shares of an ever-shrinking power budget. Mission controllers must sometimes choose between keeping instruments warm and transmitting data to Earth. The power constraints have driven remarkable innovations in low-power electronics and adaptive power management. Modern outer solar system spacecraft use sophisticated computer systems that can automatically adjust power consumption based on available energy, prioritizing critical systems during power shortages, and maximizing scientific operations when energy budgets allow. Some missions have experimented with alternative power sources. The Juno mission to Jupiter uses massive solar arrays, the largest ever deployed on a planetary mission, to gather enough solar energy to operate in Jupiter's vicinity. But even Juno's enormous solar panels, which would power a small neighborhood on Earth, provide only marginal power at Jupiter's distance. Says Euaimoniares, the mission to Jupiter uses massive solar arrays, the largest ever deployed on a planetary mission, to gather a nova. Advanced missions are exploring even more exotic power sources. Nuclear reactors designed for space use could provide much more power than RTGs, enabling more sophisticated instruments and even electric propulsion systems for outer solar system missions. But these technologies remain experimental and politically controversial. The power problem perfectly illustrates the resource constraints that define outer solar system exploration. Unlike Earth orbit missions, where power is abundant and problems can be solved by adding more solar panels or batteries, outer solar system missions must operate within strict energy budgets that only become more restrictive over time. Every successful mission represents a triumph of engineering efficiency, where scientists and engineers have learned to extract maximum scientific return from minimum power consumption. In the end, the fading power supplies of our outer solar system pioneers become poetic metaphors for the missions themselves. Gradual farewells, as these mechanical ambassadors slowly lose their voices in the cosmic dark, having whispered humanity's first words about the most distant worlds we may ever visit. In the end, the fading power supplies of our outer solar system pioneers become poetic metaphors for the missions themselves. Gradual farewells of the A's in you. Imagine trying to have a conversation with someone standing on the opposite side of a football field while you're both whispering, and there's a hurricane between you. Now multiply that football field by several billion. Replace the hurricane with the electromagnetic noise of an entire galaxy, and you begin to understand the communication challenge faced by outer solar system missions. At Neptune's distance, a spacecraft's radio signal must travel over 2.8 billion miles to reach Earth, a journey that takes over 4 hours at the speed of light. But distance is only part of the problem. Radio signals follow the same inverse square law that governs solar energy. Double the distance, and the signal strength drops to 1/4. By the time a transmission from the outer solar system reaches Earth, it's been weakened by factors of millions or billions. The actual signal strength is almost incomprehensibly weak. When Voyager 1 transmits from interstellar space, its signal arrives at Earth carrying less energy than it would take to power a digital watch for a fraction of a second. In fact, the total energy received from Voyager 1 over its entire mission, more than 4 decades of continuous transmission, is less than the energy required to turn a single page of a book. Detecting these whisper-quiet signals requires some of the most sensitive radio receivers ever built. NASA's Deep Space Network consists of enormous dish antennas, some over 200 feet in diameter, located in California, Spain, and Australia. These massive ears are pointed skyward constantly, straining to hear the faint radio whispers of humanity's most distant ambassadors. The receivers are so sensitive, they could detect the radiation from a cell phone on Jupiter. But sensitivity alone isn't enough. The antennas must track spacecraft moving at tens of thousands of miles per hour across backgrounds of cosmic radio noise. They must distinguish genuine spacecraft signals from interference created by everything from terrestrial radio stations to distant galaxies. And they must do all this while the Earth rotates, requiring a global network of antennas to maintain continuous contact as spacecraft pass in and out of view. The spacecraft themselves must be equally sophisticated communicators. Their transmitters must focus radio energy into tight beams aimed precisely at Earth across billions of miles of space. This requires knowing exactly where Earth will be, not where it is now, but where it will be when the signal arrives hours later. The pointing accuracy required is equivalent to hitting a dime with a laser pointer from a distance of several miles. Signal timing becomes critical over interplanetary distances. Commands sent to outer solar system spacecraft often take hours to arrive, and acknowledgement signals take just as long to return to Earth. If mission controllers detect a problem, they might wait 8 hours just to confirm that their corrective commands were received and executed. For time-critical operations like planetary flybys, this delay means spacecraft must be programmed to operate autonomously, making split-second decisions without human intervention. The communication challenges multiply when spacecraft venture behind planets or pass through regions of intense electromagnetic interference. Jupiter's massive magnetosphere can disrupt radio signals, creating communication blackouts that last for hours. Saturn's rings scatter radio waves, making communication difficult during close approach phases of ring studies. Even the Sun itself can interfere with communications when spacecraft, Earth, and the Sun align in ways that block or distort radio signals. These constraints have driven the development of increasingly sophisticated data compression and error correction techniques. Spacecraft must package their precious scientific data into the most efficient possible formats, using advanced algorithms to compress images and measurements without losing critical information. They must also add redundancy to their transmissions, sending the same data multiple times in different formats to ensure it survives the journey through space intact. Perhaps most remarkably, outer solar system missions have pioneered techniques for squeezing maximum information from minimum signal strength. Deep space missions use sophisticated modulation schemes that pack more data into each transmitted bit, and they employ error-correcting codes so robust that receivers can reconstruct perfect data even when significant portions of the original signal are lost to noise or interference. The human element of deep space communication is equally impressive. Teams of engineers and technicians work around the clock to maintain contact with distant spacecraft, adjusting antenna pointing, modifying receiver settings, and troubleshooting communication problems across interplanetary distances. They develop intimate knowledge of each spacecraft's communication quirks and capabilities, learning to interpret subtle changes in signal strength or data patterns that might indicate developing problems. As our mechanical ambassadors venture ever farther from home, communication becomes increasingly precious and poignant. Each successful data transmission represents a minor miracle of engineering persistence, a whispered message from the edge of the known universe, carrying humanity's first glimpses of worlds we may never visit in person. These faint radio signals, weaker than the electromagnetic signature of a lightning bolt on the opposite side of Earth, carry within them some of the most profound discoveries in human history. The communication links to our outer solar system missions are more than just engineering achievements. They're the technological umbilical cords that connect human curiosity to the most distant realms of our cosmic neighborhood, allowing us to see through the electronic eyes and hear through the digital ears of machines that have traveled farther than any human has ever dreamed of going. Jupiter doesn't just dominate the outer solar system, it essentially is the outer solar system. This single world contains more mass than all other planets combined, generates more energy than it receives from the Sun, and commands a gravitational empire that stretches millions of miles in every direction. Approaching Jupiter isn't like visiting a planet, it's like approaching a failed star, a gravitational monster whose influence shapes the architecture of our entire cosmic neighborhood. The scale becomes apparent long before you arrive. Jupiter's magnetosphere, the bubble of magnetic field that surrounds the planet, extends farther from Jupiter than the Sun's surface extends from its core. If you could see Jupiter's magnetic field with your naked eye, it would appear larger than the full moon as viewed from Earth. This invisible empire captures charged particles from the solar wind and accelerates them to nearly the speed of light, creating one of the most lethal radiation environments in the solar system. As spacecraft approach this giant, they enter a realm where the familiar rules of planetary science break down entirely. Jupiter generates almost twice as much energy as it receives from the Sun, radiating heat from its interior like a dying ember from the solar system's formation 4.6 billion years ago. As spacecraft approach this giant, they enter a realm where the familiar rules of planetary science break down entirely. This internal heat drives atmospheric dynamics, so violent they dwarf anything on Earth. Storms larger than our entire planet persist for centuries, and winds exceed 400 miles per hour in jet streams that circle the globe. The planet's immense gravity creates tidal forces that would tear apart any spacecraft venturing too close to its cloud tops. The same forces that flex Jupiter's moons, heating their interiors and driving geological activity, would stretch and compress any visitor beyond its structural limits. This invisible tidal zone extends thousands of miles above Jupiter's atmosphere, creating a keep-out zone larger than most planets. But perhaps most intimidating is Jupiter's role as the solar system's vacuum cleaner. Its immense gravitational pull captures or deflects comets, asteroids, and other debris that might otherwise threaten the inner planets. This protective function has likely prevented countless impacts on Earth throughout geological history, but it also means that approaching Jupiter requires navigating through a minefield of captured objects, many too small to detect until they're dangerously close. The visual approach to Jupiter is simultaneously beautiful and terrifying. The planet's cloud bands, visible through even small telescopes from Earth, resolve into intricate structures of staggering complexity. Each band contains multiple jet streams, vortices, and storm systems that dwarf terrestrial weather patterns. The Great Red Spot, a single storm that has raged for at least 300 years, is larger than Earth and contains enough energy to power human civilization for thousands of years. Jupiter's moons add another layer of complexity to any approach. The four largest, Io, Europa, Ganymede, and Callisto, are worlds in their own right, each presenting unique challenges and opportunities. Io's volcanic activity makes it the most geologically active body in the solar system, spewing sulfur compounds that coat nearby space with a thin but corrosive atmosphere. Europa's icy surface conceals an ocean that may contain more water than all of Earth's oceans combined. The gravitational dynamics around Jupiter are unlike anything else in the solar system. The planet's 79 known moons create a complex web of gravitational resonances, where orbital periods are locked in mathematical relationships that have persisted for billions of years. Navigating this system requires extraordinary precision, as small errors in trajectory can be amplified by gravitational perturbations until spacecraft end up millions of miles from their intended destinations. For any spacecraft attempting to orbit Jupiter, the approach phase determines the entire mission's success or failure. There are no second chances at Jupiter. The planet's immense gravity means that spacecraft get only one opportunity to execute their orbital insertion burn perfectly. Miss the narrow window for orbit insertion, and the spacecraft will either crash into Jupiter's atmosphere or be flung out of the system entirely, never to return. The approach to Jupiter also reveals the planet's subtle but profound influence on the entire solar system. Jupiter's gravity has cleared its orbital zone of debris, creating the asteroid belt through gravitational resonances that prevent small objects from coalescing into planets. Its migration early in solar system history may have triggered the late heavy bombardment, a period of intense asteroid and comet impacts that scarred the surfaces of the inner planets. Mission planners approaching Jupiter must account for all these factors: the deadly radiation, the complex gravitational environment, the risk of debris impacts, and the precise timing required for successful orbit insertion. They must design trajectories that maximize scientific observations while minimizing exposure to harmful radiation, often requiring spacecraft to thread narrow corridors between Jupiter's radiation belts and its extensive moon system. Approaching Jupiter represents humanity's first encounter with a truly alien world, a place where the physics operate on scales that dwarf terrestrial experience, and where the very concept of a surface becomes meaningless. It's a world that challenges our understanding of planetary formation, atmospheric dynamics, and the potential for life in extreme environments. Every successful approach to Jupiter represents a triumph over forces that could casually destroy entire civilizations, a testament to human ingenuity, navigating the most extreme gravitational and electromagnetic environment in our solar system. The monster at the gates of the outer solar system demands respect, precision, and a healthy appreciation for the awesome forces that govern our cosmic neighborhood. Jupiter doesn't just have a radiation problem. It is a radiation problem wrapped in 300 Earth mass package and decorated with beautiful cloud bands that hide one of the most lethal environments in the solar system. The radiation belts surrounding Jupiter contain enough high-energy particles to kill an unprotected human in minutes and destroy most electronic equipment in hours. To understand why exploring Jupiter is so challenging, you must first grasp the invisible hell that surrounds this deceptively beautiful giant. The story begins with Jupiter's magnetic field, which is absolutely colossal. Earth's magnetic field, which protects us from solar radiation and cosmic rays, extends about 60,000 miles into space. Jupiter's magnetic field is 20,000 times stronger and extends over 600 million miles, so far that it sometimes engulfs Saturn when the two planets are aligned properly. If you could see magnetic field lines with your naked eye, Jupiter's magnetosphere would appear 5 times larger than the full moon as viewed from Earth. This enormous magnetic field acts like a cosmic particle accelerator, trapping charged particles from the solar wind and accelerating them to tremendous energies. But Jupiter's radiation environment is far more complex than Earth's relatively simple Van Allen belts. The planet's rapid rotation, a day on Jupiter lasts less than 10 hours, whips the magnetic field around like a cosmic blender, creating dynamic structures that can change on timescales of minutes or hours. The radiation becomes most intense in Jupiter's inner magnetosphere, particularly around the orbit of Io here. Charged particles reach energies of hundreds of millions of electron volts, levels that approach those created in humanity's most powerful particle accelerators. These particles don't just threaten spacecraft electronics, they fundamentally alter the chemical and physical properties of any materials they encounter. Io itself contributes to this radioactive nightmare. The moon's intense volcanic activity spews sulfur and oxygen atoms into space at a rate of about 1 ton per second. These atoms become ionized by Jupiter's radiation and are swept up by the planet's magnetic field, creating a donut-shaped torus of plasma that extends around Io's entire orbit. This plasma torus adds another layer of hazard for any spacecraft attempting to study Jupiter's inner moon system. The effects of this radiation on spacecraft are both dramatic and insidious. High-energy particles can flip bits in computer memory, causing software errors that might not manifest until critical moments. They gradually degrade solar cells, reducing power output over time. Most dangerously, they can cause sudden, catastrophic failures in sensitive electronic components, potentially ending missions without warning. The Galileo mission, which orbited Jupiter from 1995 to 2003, provided a sobering lesson in Jupiter's radiation hazards. Despite extensive radiation shielding, the spacecraft's camera began suffering radiation damage almost immediately upon entering Jupiter orbit. By the end of the mission, several instruments had failed entirely due to radiation exposure, and the main antenna never deployed properly, possibly due to radiation-induced degradation of its mechanism during the long journey to Jupiter. Engineering spacecraft to survive in Jupiter's radiation environment requires a complete reimagining of traditional spacecraft design philosophies. Electronic components must be specially hardened against radiation, often using older, less efficient technologies that are more resistant to particle bombardment. Critical systems require multiple layers of shielding, typically using materials like tantalum or lead that can absorb high-energy particles before they reach sensitive electronics. But shielding comes at a tremendous cost in mass and complexity. Every pound of radiation shielding is a pound that can't be used for scientific instruments, fuel, or other mission-critical systems. Mission designers must perform a delicate balancing act, providing enough protection to ensure mission success, while keeping the spacecraft light enough to launch and operate effectively. The Juno mission, currently orbiting Jupiter, represents the state-of-the-art in radiation-hardened spacecraft design. Juno's electronics are housed within a titanium vault that provides 360-degree protection from Jupiter's particle bombardment. The vault weighs over 400 pounds, more than many entire spacecraft, but it allows Juno's instruments to survive in Jupiter's inner magnetosphere for extended periods. Even with extensive shielding, missions to Jupiter must carefully plan their trajectories to minimize radiation exposure. Spacecraft often follow highly elliptical orbits that spend most of their time in the relatively safe outer magnetosphere, diving briefly into the high radiation zones only when necessary for specific scientific observations. These radiation-conscious trajectories can significantly complicate mission planning and limit scientific opportunities. The radiation environment also creates unique operational challenges. During passages through Jupiter's most intense radiation belts, mission controllers often place spacecraft in safe mode, shutting down non-essential systems and putting sensitive instruments into protective configurations. These radiation-induced communication blackouts can last for hours, during which ground controllers can only wait and hope their spacecraft emerge unscathed. Perhaps most remarkably, Jupiter's radiation environment is dynamic and unpredictable. Solar activity can inject additional particles into Jupiter's magnetosphere, creating radiation storms that far exceed normal levels. Volcanic eruptions on Io can alter the plasma environment around Jupiter, creating new hazards for orbiting spacecraft. Mission planners must design for worst-case scenarios while hoping for the best. The radiation challenge at Jupiter also highlights the fundamental limitations of human exploration in the outer solar system. While robotic spacecraft can be hardened to survive in Jupiter's radiation environment for limited periods, humans would require massive shielding or completely new technologies to survive even brief visits to Jupiter's vicinity. The radiation doses near Jupiter are thousands of times higher than what astronauts experience on the International Space Station. Despite these challenges, each successful mission to Jupiter teaches us more about operating in extreme radiation environments. The engineering solutions developed for Jupiter missions have applications for future missions to other highly irradiated environments, including the moons of the outer planets, and eventually, perhaps, interstellar destinations where cosmic radiation poses similar challenges. Jupiter's radiation hell represents one of the most severe environmental challenges faced by any space mission. It's an invisible enemy that can destroy millions of dollars of equipment in seconds, end missions without warning, and fundamentally limit how we explore the most massive planet in our solar system. Yet overcoming this challenge has pushed the boundaries of engineering and opened windows into a world that continues to revolutionize our understanding of planetary formation, magnetic field dynamics, and the potential for life in extreme environments. Every image returned from Jupiter's vicinity, every measurement of its magnetic field, every discovery about its moons represents a victory over one of the most hostile environments in our solar system, a testament to human ingenuity triumphing over radiation levels that would sterilize entire worlds. 400 years ago, when Galileo Galilei first pointed his primitive telescope at Jupiter, he discovered 4 tiny points of light that would revolutionize humanity's understanding of the universe. Those 4 moons, Io, Europa, Ganymede, and Callisto, not only proved that Earth wasn't the center of everything, but they would eventually reveal that our solar system contains worlds more exotic, more geologically active, and more potentially habitable than anyone had ever imagined. Go. The first close-up images from Voyager, one in 1979, turned Jupiter's moons from telescopic curiosities into genuine worlds. Io emerged as the most volcanically active body in the solar system, its surface painted in garish yellows and reds by sulfur compounds ejected from over 400 active volcanoes. The tidal heating caused by Jupiter's immense gravity literally turns Io inside out every few million years, creating a world where the ground itself is molten and the atmosphere consists of sulfur dioxide snow. But it was Europa that truly changed everything. Beneath its cracked, icy surface lies an ocean containing more than twice as much water as all of Earth's oceans combined. This isn't just any water, it's liquid water that has existed for billions of years, kept from freezing by the same tidal heating that drives Io's volcanoes. The ice shell above shows clear evidence of geological activity, ridges, cracks, and strange terrain features that suggest the ocean below is in contact with the surface above. The implications hit the scientific community like a thunderbolt. For centuries, astronomers had assumed that life, if it existed anywhere else, would be found on worlds similar to Earth, rocky planets orbiting at just the right distance from their stars to maintain liquid water on their surfaces. Europa shattered this assumption entirely. Here was a world farther from the sun than Mars, locked in eternal winter, yet harboring conditions that might support life. Ganymede, the largest moon in the solar system, revealed its own secrets. Despite being bigger than Mercury, Ganymede possesses a magnetic field generated by a molten iron core, something that should be impossible for such a small world so far from the sun, like Europa. Ganymede appears to harbor a subsurface ocean, adding another potentially habitable environment to Jupiter's collection of hidden worlds. Even Callisto, the most distant and ancient of Jupiter's large moons, shows evidence of a subsurface ocean beneath its heavily cratered surface. Its ice-rich composition and lack of geological activity make it a pristine record of the early solar system. Yet even this ancient world may harbor the conditions necessary for life. The discovery of these subsurface oceans fundamentally changed astrobiology, the study of potential life beyond Earth. Scientists realized that the habitable zone around stars, where liquid water can exist on planetary surfaces, represented only a tiny fraction of potentially life-supporting environments. Icy moons with subsurface oceans could exist throughout the outer solar system, around any planet massive enough to generate tidal heating. This revelation transformed Jupiter from a beautiful but sterile gas giant into the center of a system containing more potentially habitable worlds than the entire inner solar system. The 4 Galilean moons alone might harbor more liquid water than Earth, Mars, Venus, and Mercury combined. And if life exists in these hidden oceans, it would represent a completely independent genesis of biology, a second tree of life that evolved entirely separately from Earth's biosphere. The moons also revealed the incredible diversity of geological processes operating in the outer solar system. Io's sulfur volcanism creates landscapes unlike anything on Earth. Europa's ice tectonics produces terrain features that have no terrestrial analogues. Ganymede's magnetic field interactions with Jupiter create auroras more spectacular than anything seen on Earth. Each moon represents a unique laboratory for studying planetary processes under conditions impossible to replicate in our own neighborhood. Perhaps most importantly, Jupiter's moons demonstrated that small worlds can remain geologically active for billions of years if they're subject to the right external forces. This insight revolutionized our understanding of habitability throughout the galaxy. Rocky planets around distant stars might become tidally locked and frozen, but their moons could remain dynamic and potentially habitable for the entire lifetimes of their parent stars. The Galilean satellites transformed Jupiter from a solitary giant into the capital of a diverse system of worlds, each with its own personality, geological history, and potential for harboring life. They showed us that the outer solar system isn't a cold, dead wasteland, but a frontier containing some of the most intriguing and potentially habitable environments in our cosmic neighborhood. In discovering these moons, we discovered that the universe is far more creative, more dynamic, and more potentially alive than we had ever dared to imagine. Saturn stops conversations. Even seasoned astronomers, who have seen the planet thousands of times through telescopes, still pause in wonder when Saturn swims into view. There's something about those rings that transcends scientific curiosity and enters the realm of pure aesthetic amazement. They shouldn't exist. They can't be permanent. Yet there they are, a cosmic impossible made manifest in ice and rock, spinning in perfect formation around a world that seems too beautiful to be real. The rings appear solid and permanent from a distance, but they're actually composed of countless individual particles, from tiny ice crystals, smaller than snowflakes, to house-sized boulders, each following its own independent orbit around Saturn. These particles range in composition from nearly pure water ice to rocky debris, creating subtle color variations across the ring structure that speak to complex histories of collision, accretion, and gravitational shepherding. What makes Saturn's rings truly impossible is their thinness. The main rings span nearly 200,000 miles from edge to edge, 3/4 the distance from Earth to the Moon, yet they're only about 30 feet thick. If you could shrink Saturn's rings down to the size of a compact disk, they'd be 1,000 times thinner than a sheet of paper. This extraordinary flatness results from countless collisions between ring particles over millions of years, gradually flattening their orbits into a single gossamer-thin plane. The rings shouldn't be there at all. According to our best understanding of planetary formation, ring systems should be temporary features that dissipate relatively quickly. Tidal forces from the planet should pull ring particles inward, while interactions with the planet's moons should scatter them outward. Computer models suggest that Saturn's rings should disappear within a few 100 million years, a brief moment in the 4.6 billion-year history of the solar system. Yet there they are, and recent evidence suggests they might be much younger than previously thought. The Cassini mission's final dive through Saturn's rings revealed that they contain very little rocky debris, far less than would be expected if they had been accumulating meteoritic dust for billions of years. This suggests Saturn's rings might be only 100–400 million years old, formed during the age of dinosaurs on Earth, from the breakup of a large moon or captured comet. The ring system displays structure so intricate it defies comprehension. What appear as simple bands through Earth-based telescopes resolve into thousands of individual ringlets, each with its own orbital characteristics. Some rings are held in place by tiny shepherd moons that gravitationally confine the particles. Others show spiral density waves created by resonances with Saturn's larger moons, gravitational influences that propagate through the rings like ripples on a cosmic pond. Perhaps most mysteriously, the rings show spokes, radial features that appear and disappear on timescales of hours. These spokes seem to violate the basic laws of orbital mechanics, as they maintain their radial orientation despite the fact that inner ring particles orbit faster than outer ones. The spokes appear to be caused by electromagnetic forces that temporarily lift tiny particles above the ring plane, creating ghostly features that come and go like aurora on Saturn's rings. The rings also demonstrate the incredible precision of gravitational mechanics. Some ringlets are only a few miles wide, held in stable orbits for millions of years by gravitational resonances with distant moons. The particles in these narrow rings must maintain almost perfect orbital velocities, differ by more than a few inches per second, and they would either spiral inward towards Saturn or escape outward into space. Saturn's rings represent a natural laboratory for studying gravitational physics, orbital mechanics, and particle dynamics on scales impossible to replicate on Earth. Every spoke, gap, and ringlet tells a story about how gravity shapes matter over vast scales and long timescales. The rings are simultaneously ancient and ephemeral, massive and delicate, chaotic and perfectly ordered. The beauty of Saturn's rings isn't just aesthetic. It's the beauty of physical laws made visible, of mathematical relationships expressed in ice and stone. They remind us that the universe can create structures of stunning elegance through nothing more than gravity, time, and the relentless dance of countless particles following the invisible choreography of celestial mechanics. Standing in Saturn's shadow, looking back at the ring's edge on, reveals them as gossamer threads of light catching the distant sun. From this perspective, Saturn's impossible beauty becomes even more profound, a reminder that some of the universe's most magnificent creations are also its most fragile, temporary masterpieces, written in cosmic ice and destined to fade like morning frost on a planetary scale. Titan shouldn't feel familiar, yet it does. This giant moon of Saturn, shrouded in an atmosphere thicker than Earth's, and chilled to temperatures that would freeze nitrogen solid, somehow manages to feel like a distorted reflection of our own world. It has lakes and rivers, beaches and coastlines, weather and seasons, all the geographic features that make Earth feel like home, except they're composed of liquid methane and ethane instead of water, and the rocks are made of water ice, harder than granite. The first hints of Titan's strange familiarity came from Voyager 1 in 1980, when the spacecraft's cameras revealed a world completely shrouded in orange-brown haze. Unlike any other moon in the solar system, Titan possessed a substantial atmosphere, not just a thin envelope of gas like Mars, but a thick, substantial atmosphere with 50% higher surface pressure than Earth's. The atmosphere was primarily nitrogen, just like Earth's, but with one crucial difference. Instead of oxygen as the secondary component, Titan's atmosphere contained methane, ethane, and complex organic compounds that created the opaque haze, blocking our view of the surface. That haze became both a tantalizing mystery and a frustrating barrier. For over 2 decades, scientists could only speculate about what lay beneath Titan's orange veil. Theoretical models suggested the surface might be covered with lakes or oceans of liquid methane, but proving this required getting below the atmosphere to see the surface directly. The Cassini mission, which arrived at Saturn in 2004, carried infrared cameras that could peer through Titan's haze at specific wavelengths. What they revealed was nothing short of extraordinary. A world with dark regions that looked suspiciously like lakes, bright areas resembling continents, and sinuous features that could only be river systems. Here was a moon that had lakes, rivers, and what appeared to be an active hydrological cycle, except instead of water, it was all liquid hydrocarbons. The true revelation came on January 14, 2005, when the Huygens probe, carried to Titan aboard Cassini, descended through the moon's atmosphere and landed on the surface. During its 2.5-hour descent, Huygens transmitted images that could have been taken during a flight over Earth. If you could ignore the alien color palette, the probe's cameras revealed drainage networks, riverbeds, and what appeared to be a shoreline with rounded cobbles, features carved by flowing liquids over geological time. The surface where Huygens landed was simultaneously alien and familiar. The soil was composed of water ice particles and organic compounds, the consistency of damp sand, but at temperatures of -290 degrees Fahrenheit, -179 degrees Celsius. The rocks were chunks of water ice, harder than stone at Titan's surface temperature. The landscape showed clear evidence of fluvial activity, channels carved by flowing liquid, sediment deposits, and erosional features that spoke of dynamic geological processes. Subsequent observations by Cassini revealed the full scope of Titan's alien water cycle. The moon has vast lakes near its poles, filled with liquid methane and ethane. These lakes change size and shape over time, indicating active evaporation and precipitation. Titan experiences seasons as Saturn orbits the Sun, and these seasonal changes drive weather patterns that create methane clouds, hydrocarbon rain, and seasonal lake level variations. The methane cycle on Titan parallels Earth's water cycle in remarkable detail. Liquid methane evaporates from lakes and seas, rises into the atmosphere, condenses into clouds, and falls as methane rain that carves riverbeds and fills lakes. But the timescales are different. Titan receives only 1% as much solar energy as Earth, so the processes operate much more slowly. A rainstorm on Titan might last for days or weeks, and the carved landscapes preserve their features for millions of years. Perhaps most intriguingly, Titan possesses something no other moon in the solar system has: a substantial inventory of organic compounds. The atmosphere's methane and nitrogen interact with solar ultraviolet light and charged particles from Saturn's magnetosphere to create complex organic molecules, the building blocks of biochemistry. These compounds rain down onto Titan's surface, where they accumulate over geological time to create deposits of organic material thousands of feet thick. This organic chemistry makes Titan one of the most intriguing astrobiological targets in the solar system. While the surface is far too cold for Earth-like life, the Moon might harbor subsurface liquid water oceans, similar to Europa and Enceladus, that could provide more temperate conditions for biology. Even more speculatively, some scientists have wondered whether exotic forms of life might exist in Titan's hydrocarbon lakes, using liquid methane as a solvent instead of water. Titan's familiar strangeness extends to its geology, or the Moon experiences cryovolcanism, ice volcanoes that erupt liquid water and ammonia instead of molten rock. These eruptions create geological features that resemble terrestrial volcanoes, but operate at temperatures hundreds of degrees below the freezing point of water. The surface shows evidence of tectonic activity, erosion, and deposition, all the geological processes that shape terrestrial planets, but operating with exotic materials under alien conditions. Dunder's familiar stroses that resemble terrestrial volcanoes, but operate at temperatures hundreds of degrees below the freezing point of water. The atmospheric dynamics on Titan are equally fascinating. The thick atmosphere supports complex weather patterns, including cloud formation, precipitation, and wind systems that transport organic compounds around the globe. The atmosphere is so thick that humans could walk on Titan's surface without pressure suits, though they would still need heating and oxygen to survive the frigid, toxic environment. Titan represents a natural laboratory for studying how familiar planetary processes operate under completely different conditions. It's a world where the physics of fluid flow, atmospheric circulation, and geological evolution create landscapes that look surprisingly familiar, yet are composed of materials that would be gaseous on Earth. It challenges our Earth-centric assumptions about habitability and planetary evolution, while simultaneously demonstrating the universality of physical processes that shape worlds throughout the cosmos. In many ways, Titan feels like Earth's distant cousin, similar enough that we recognize the family resemblance, yet different enough to remind us of the incredible diversity of worlds that exist in our own solar system. It's a place where familiar processes create alien landscapes, where the impossible becomes routine, and where the boundaries between the familiar and the fantastic dissolve in methane rain under an orange sky. Titan proves that the universe's creativity extends far beyond our terrestrial experience, creating worlds that challenge our imagination while operating according to the same physical laws that govern our own planet. It's both alien and familiar, impossible and inevitable, a perfect example of how the cosmos continues to surprise us in the most beautiful and unexpected ways. In 2005, a small icy moon, barely 300 miles across, rewrote the textbook on where life might exist in our solar system. Enceladus, Saturn's sixth largest moon, had been dismissed as a frozen, geologically dead ice ball, just another crater-scarred remnant from the early solar system. Then Cassini arrived, and everything we thought we knew about small worlds, subsurface oceans, and the potential for life beyond Earth changed forever. The first hint that Enceladus was special came from temperature readings that made no sense. The moon's south polar region was significantly warmer than it should be, not just by a few degrees, but by tens of degrees warmer than models predicted. This was particularly puzzling because Enceladus orbits Saturn at the same distance as our Moon orbits Earth, receiving only 1% of the sunlight Earth gets. There was no obvious reason for the South Pole to be generating its own heat. The mystery deepened when Cassini's cameras revealed that the South Polar region looked completely different from the rest of Enceladus. While most of the Moon's surface was heavily cratered and ancient, the South Pole was smooth, relatively crater-free, and marked by a series of parallel fractures nicknamed tiger stripes. These fractures appeared young, possibly active, which seemed impossible for such a small, distant world. Then came the discovery that changed everything. On July 14, 2005, Cassini detected something unprecedented: plumes of water vapor and ice particles erupting from the tiger stripe fractures on Enceladus's south pole. These weren't just small outgassings, they were massive geysers shooting material hundreds of miles above the surface, creating a tenuous atmosphere around the Moon and feeding particles into Saturn's E-ring. The implications hit the scientific community immediately. The fact that Enceladus could maintain liquid water beneath its icy crust meant that this tiny moon harbored conditions that might support life, not in some distant future or ancient past, but right now. Subsequent flybys revealed the full extent of Enceladus's hidden ocean. Gravitational measurements indicated that beneath the Moon's 20-mile-thick ice shell lies a global ocean containing more water than Lake Superior. This ocean is in direct contact with Enceladus's rocky core, creating the potential for hydrothermal activity similar to the deep-sea vents on Earth that may have been crucial for the origin of life. The chemistry of the plumes told an even more intriguing story. Cassini's instruments detected not just water vapor, but also organic compounds, nitrogen, and most significantly, hydrogen gas. The hydrogen is particularly important because it's produced by hydrothermal reactions between water and rock, the same processes that sustain entire ecosystems around Earth's deep-sea hydrothermal vents, far from sunlight and photosynthesis. What makes Enceladus truly revolutionary is that it represents a completely accessible ocean, while Europa's subsurface ocean lies beneath miles of solid ice that would require complex drilling operations to reach. Enceladus brings its ocean directly to us. Every time the Moon erupts, it's essentially sampling its own ocean and delivering the results to space, where passing spacecraft can analyze them. It's like having a natural laboratory that provides its own samples for analysis. The energy source driving Enceladus's activity is tidal heating, the same gravitational flexing that powers Io's volcanoes and Europa's ocean. As Enceladus orbits Saturn in an elliptical path, the planet's gravity alternately squeezes and stretches the Moon, generating heat through friction. This tidal heating is concentrated in the South Polar region due to the Moon's orbital characteristics and internal structure, explaining why the geysers are localized to that area. The discovery of Enceladus's ocean fundamentally changed astrobiology. Here was direct evidence that small, icy moons could maintain habitable conditions for billions of years. The findings suggested that subsurface oceans might be common throughout the outer solar system, potentially making icy moons more numerous potential habitats for life than Earth-like planets. Enceladus also demonstrated that we could study extraterrestrial oceans without landing on the surface or drilling through miles of ice. The plume material contains everything we need to understand the ocean's chemistry, temperature, salinity, and potential for life. Future missions could potentially detect biosignatures, chemical evidence of life, simply by flying through the plumes and analyzing the ejected material. The Moon's small size actually works in its favor for maintaining a habitable environment. Unlike larger worlds where tidal heating might drive excessive volcanism, Enceladus's modest size allows for a delicate balance between energy input and heat loss. The result is an environment that's warm enough to maintain liquid water, but stable enough to persist for geological timescales. The geological timescales. Recent studies have revealed even more intriguing details about Enceladus's ocean. The water appears to be alkaline and rich in dissolved salts, conditions that would be highly favorable for certain types of life. The ocean's interaction with the rocky core might produce chemical gradients and energy sources similar to those that support life in Earth's deep ocean environments. Enceladus represents the democratization of astrobiology. You don't need to be a gas giant or orbit in the habitable zone of a star to potentially harbor life. You just need the right combination of water, energy, and chemistry, conditions that might exist on dozens of moons throughout our solar system and countless more around other stars. In revolutionizing our understanding of habitability, Enceladus transformed from an insignificant ice ball into one of the most important targets for astrobiology in our solar system. It proved that the universe's potential for life extends far beyond Earth-like worlds, encompassing environments so exotic and unexpected that they challenge our most basic assumptions about where life might arise and thrive. Uranus is the solar system's ultimate enigma, a world so bizarre that it seems to mock our understanding of how planets should behave. While every other planet in the solar system spins roughly upright like a spinning top, Uranus lies on its side, rolling through space like a cosmic bowling ball. Uranus lies on its side, rolling through space like a cosmic bowling ball. Its rotational axis is tilted 98 degrees from vertical, not just tilted, but completely knocked over, spinning backward compared to most other worlds. This sideways orientation creates the most extreme seasons imaginable. During Uranus's 84-year orbit around the Sun, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. Imagine a world where winter lasts for decades, where the sun doesn't rise for an entire human generation, and where the very concept of day and night becomes meaningless at the poles. It's a planetary nightmare of perpetual seasonal extremes. The cause of Uranus's sideways spin remains one of the great unsolved mysteries of planetary science. The most widely accepted theory suggests that during the early formation of the solar system, Uranus was struck by an Earth-sized object, a collision so catastrophic that it knocked the entire planet onto its side. But this explanation creates new puzzles. Such a massive impact should have disrupted Uranus's moons and rings, yet they orbit in the same tilted plane as the planet's equator, as if they formed after the collision or somehow survived the chaos intact. When Voyager 2 made its historic flyby of Uranus in January 1986, it revealed a world that defied expectations in almost every way. Scientists expected to find a dynamic, weather-rich atmosphere like those of Jupiter and Saturn, but Uranus appeared almost featureless, a bland blue-green disk with barely any visible cloud formations or atmospheric activity. The planet seemed geologically and meteorologically dead, earning it the nickname the boring planet. But Uranus's apparent blandness masked deeper mysteries. The planet's magnetic field was completely unexpected, tilted 60 degrees from the rotational axis, and offset from the planet's center by nearly 1/3 of the planet's radius. This bizarre magnetic geometry suggests that the magnetic field is generated not in the planet's core, but in its outer layers, possibly in a shell of conducting water and ammonia ice surrounding a small rocky core. The atmospheric composition of Uranus added another layer of strangeness. While Jupiter and Saturn are primarily hydrogen and helium, with traces of other compounds, Uranus contains significant amounts of water, methane, and ammonia ices. These materials give the planet its distinctive blue-green color, as methane absorbs red light and reflects blue and green wavelengths back to space. But the abundance of these ices at Uranus's distance from the Sun suggests the planet formed through processes quite different from those that created the larger gas giants. Perhaps most mysteriously, Uranus radiates almost no excess heat into space. Jupiter and Saturn both emit more energy than they receive from the Sun, gradually cooling from their hot formation. Neptune, farther from the Sun than Uranus, radiates 2.6 times more energy than it receives. But Uranus emits almost exactly the same amount of energy it absorbs from solar radiation, suggesting it has no significant internal heat source. This thermal puzzle remains unexplained. Either Uranus formed differently than other giant planets, or the catastrophic impact that tilted it also affected its internal heat budget. The discovery of Uranus's ring system in 1977 added another chapter to the planet's story of unexpected discoveries. Unlike Saturn's broad, bright rings composed primarily of ice, Uranus's rings are narrow, dark, and composed of organic compounds that have been altered by radiation over millions of years. These rings are so dark, they reflect only 2% of the sunlight that hits them, darker than charcoal. They're also incredibly thin, some only a few miles wide, held in place by small shepherd moons that prevent the ring particles from spreading out. The moons of Uranus tell their own tale of violence and disruption. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, show evidence of complex geological histories despite their small sizes and great distance from the Sun. Miranda, in particular, appears to have been completely shattered and reassembled at least once during its history, creating a patchwork surface that combines ancient, heavily cratered terrain with younger grooved regions that suggest the Moon was geologically active long after it should have frozen solid. Uranus challenges our models of planetary formation and evolution at every turn. Sideways orientation affects everything from atmospheric circulation to magnetic field generation to seasonal weather patterns. The planet experiences solar heating patterns, unlike anywhere else in the solar system, with poles that are alternately baked and frozen over decades-long cycles. Recent observations have revealed that Uranus isn't as bland as Voyager 2 suggested. As the planet approaches its equinox, when the Sun shines directly on the equator for the first time in decades, atmospheric activity has increased dramatically. Bright clouds have appeared in the atmosphere, and the planet shows signs of complex weather systems that were invisible during Voyager's brief encounter. The ice giants like Uranus may actually be the most common type of planet in the galaxy. Recent exoplanet surveys suggest that worlds with masses between Neptune and Earth, the so-called super-Earths and mini-Neptunes, are extremely abundant around other stars. Understanding Uranus and Neptune might provide insights into the most typical planetary environments in the cosmos, even though they represent the most exotic worlds in our own solar system. Uranus remains a world that refuses to fit into neat categories, a planet that challenges every assumption about how worlds should behave, and reminds us that the universe's creativity extends far beyond our terrestrial experience. Neptune shouldn't have weather. Located 30 times farther from the Sun than Earth, this distant world receives less than 1,000th of the solar energy that drives our planet's atmospheric systems. At such enormous distance from our star, Neptune should be a frozen, inactive ice ball, its atmosphere locked in perpetual stasis by the cold of deep space. Instead, Neptune hosts the most dynamic, violent weather in the entire solar system, with wind speeds that exceed the speed of sound and storms that dwarf anything Earth has ever experienced. Nosa, uns conservcharius, to centrofcharius area soothing. When Voyager 2 encountered Neptune in August 1989, it revealed a world in constant atmospheric turmoil. The planet's most prominent feature was the Great Dark Spot, a storm system larger than Earth that dominated Neptune's southern hemisphere. Winds around this massive anticyclone reached speeds of over 1,500 miles per hour, making them the fastest winds ever measured on any planet. To put this in perspective, these winds are 3 times faster than the strongest hurricanes ever recorded on Earth and approach supersonic speeds in Neptune's atmospheric conditions. The energy driving these impossible winds remains one of the great mysteries of planetary science. Earth's weather systems are powered by solar heating, which creates temperature differences that drive atmospheric circulation. But Neptune receives only 0.1% of the solar energy that Earth does, barely enough to power the weakest earthly weather systems. Yet somehow, this distant world generates atmospheric dynamics that make Earth's most violent storms look gentle by comparison. The answer appears to lie in Neptune's internal heat source. Like Jupiter and Saturn, Neptune radiates more energy than it receives from the Sun, about 2.6 times more. This internal heat, left over from the planet's formation, was generated by gravitational compression, provides the energy that drives Neptune's atmospheric engine. But this only deepens the mystery. Uranus, which is closer to the Sun and similar in composition, shows almost no atmospheric activity and radiates virtually no excess heat. Why should two similar worlds behave so differently? Neptune's weather systems change with bewildering speed. The Great Dark Spot, which dominated the planet's appearance during Voyager's flyby, had completely vanished by the time the Hubble Space Telescope observed Neptune, just 5 years later. In its place, a new Great Dark Spot had appeared in the planet's northern hemisphere. These massive storm systems seem to form, evolve, and dissipate on timescales of years, incredibly rapid for atmospheric features larger than entire planets. The wind patterns on Neptune defy conventional atmospheric physics. On Earth and other planets, the fastest winds typically occur at the equator, where the planet's rotation and solar heating create optimal conditions for atmospheric circulation. But Neptune's fastest winds occur at higher latitudes, and they blow in the opposite direction to the planet's rotation. It's as if the atmosphere is actively fighting against the planet's spin, powered by some unknown energy source that remains mysterious even decades after its discovery. The atmospheric composition adds another layer of complexity. Neptune's atmosphere is primarily hydrogen and helium, with traces of methane, hydrogen sulfide, and other compounds. The methane gives Neptune its distinctive blue color, but it also plays a crucial role in the planet's atmospheric chemistry. At Neptune's cold temperatures, methane condenses into clouds at different altitudes, creating a complex layered atmosphere with multiple cloud decks and chemical processes that influence wind patterns and storm formation. Recent observations have revealed even more bizarre aspects of Neptune's atmospheric behavior. The planet shows evidence of seasonal changes despite its 165-year orbit around the Sun. Atmospheric temperatures and wind patterns vary as different hemispheres experience their decades-long seasons. The southern hemisphere has been gradually warming since Voyager's encounter, possibly due to seasonal effects that operate on timescales barely comprehensible to human experience. The interaction between Neptune's internal heat, its rapid rotation — a day lasts only about 16 hours, and its complex atmospheric chemistry creates a weather system unlike anything else in the solar system. Computer models struggle to explain how such violent atmospheric dynamics can be sustained on a world so far from the Sun, with so little external energy input. This gentle energy input, Neptune's impossible winds, challenge our understanding of atmospheric physics and planetary energy budgets. They suggest that internal heat sources can drive atmospheric dynamics far more complex and energetic than solar heating alone. This has implications for understanding exoplanets, worlds around other stars that might have their own internal energy sources, driving weather systems completely unlike anything in our solar system. The winds of Neptune remind us that distance from a star doesn't necessarily mean atmospheric death. Even in the cold depths of the outer solar system, worlds can maintain dynamic, evolving atmospheres powered by energy sources we're only beginning to understand. Neptune's storms are a testament to the universe's ability to create beauty and violence in the most unexpected places. In August 1989, Voyager 2's cameras revealed something extraordinary in Neptune's blue atmosphere, a massive dark oval, larger than Earth itself, spinning counterclockwise in the planet's southern hemisphere. The Great Dark Spot, as astronomers dubbed it, was a storm system so large and prominent that it seemed to define Neptune's very character. Yet within just 5 years, this colossal feature had completely vanished, leaving scientists to grapple with one of the most puzzling atmospheric phenomena ever observed. The Great Dark Spot wasn't just large, it was impossibly large, measuring roughly 8,000 miles across and 4,000 miles wide. It covered an area equivalent to the entire Atlantic Ocean. The storm was an anticyclone, spinning in the opposite direction to cyclones like Earth's hurricanes, with wind speeds around its periphery exceeding 1,200 miles per hour. White cirrus-like clouds, composed of frozen methane, formed and dissipated around the spot's edges, creating dynamic patterns that changed over periods of hours. In recent years, the story denti sind fortha, sidu var. What made the Great Dark Spot truly mysterious was its behavior. Unlike Jupiter's Great Red Spot, which has persisted for centuries in a relatively stable location, Neptune's Great Storm was a wanderer. During Voyager's brief encounter, astronomers observed the spot drifting westward at speeds of up to 700 miles per hour, roughly the speed of sound in Earth's atmosphere. This rapid motion suggested the storm was not anchored to any particular atmospheric layer or geographic feature, but was instead a free-floating atmospheric phenomenon. The spot's dark appearance created another puzzle. While storms on Earth and other planets typically appear as bright or differently colored features against their atmospheric backgrounds, the Great Dark Spot appeared as a hole in Neptune's atmosphere, a region where the normal blue coloration was conspicuously absent. Some scientists theorized that the spot was actually a clearance in Neptune's upper cloud layers, allowing observers to see deeper into the planet's darker, lower atmosphere. The chemistry of the spot's formation remained enigmatic. Neptune's atmosphere consists primarily of hydrogen and helium, with traces of methane, which creates the planet's characteristic blue color by absorbing red light. The white clouds associated with the Great Dark Spot were composed of methane ice crystals that formed when atmospheric methane condensed at high altitudes. But why these clouds formed preferentially around the dark spot, and what caused the spot's dark appearance, remained unclear. Temperature measurements revealed that the Great Dark Spot was actually warmer than its surroundings, a characteristic typical of anticyclonic storms. This temperature difference helped drive the spot's circulation, but it also raised questions about the energy sources sustaining such a massive atmospheric feature on a world receiving so little solar energy. The spot appeared to be powered by Neptune's internal heat, but the mechanisms converting that heat into organized atmospheric circulation remained mysterious. The spot's rapid changes fascinated atmospheric physicists. During Voyager's 4-month approach to Neptune, the Great Dark Spot changed shape, size, and rotational characteristics. The white companion clouds appeared and disappeared on timescales of days. The entire system seemed to be in constant flux, unlike the relatively stable storm systems observed on Jupiter and Saturn. Then came the shock. In 1994, when the Hubble Space Telescope turned its powerful eye toward Neptune, the Great Dark Spot had completely disappeared. The massive storm that had dominated the planet's appearance for decades, possibly centuries, was simply gone. In its place, Hubble discovered a new Great Dark Spot in Neptune's northern hemisphere, suggesting that these massive storms might be transient features that form, evolve, and dissipate on timescales of years to decades. This discovery revolutionized our understanding of atmospheric dynamics on the ice giants, unlike the gas giants, Jupiter and Saturn, whose massive storm systems can persist for centuries. Neptune appeared to host atmospheric phenomena that were dynamic, unstable, and constantly evolving. The planet's weather seemed to operate on human timescales rather than geological ones. The vanishing of the Great Dark Spot raised profound questions about Neptune's atmospheric processes. What energy sources could create such massive storms? Why do they form? And what causes them to dissipate? How can a planet so far from the Sun maintain such dynamic atmospheric activity? Computer models of Neptune's atmosphere struggled to explain how storms larger than Earth could form and disappear so rapidly. Subsequent observations have revealed that Great Dark Spots might be cyclical phenomena on Neptune. Since Hubble's first observations, astronomers have tracked the formation and evolution of multiple dark spots in different regions of Neptune's atmosphere. Some persist for years, while others disappear within months. The planet seems to maintain a population of these massive storms, with new ones forming as others fade away. The Great Dark Spot mystery highlights the limitations of snapshot observations in planetary science. Voyager 2's brief encounter with Neptune captured just one moment in the planet's dynamic atmospheric evolution. What seemed like a permanent, defining feature was actually a temporary phenomenon, a storm that happened to be visible during humanity's first and only close-up look to the universe by German physicist Rudolf Clausius in the 19th century, leading to his famous statement that the entropy of the universe tends toward a maximum. But it wasn't until the 20th century that astronomers began to understand the specific mechanisms by which cosmic entropy increases and what this means for the ultimate fate of all organized structures. Stars are perhaps the most obvious examples of entropy-increasing processes in the universe. Every second, our sun converts millions of tons of highly organized hydrogen nuclei into slightly less organized helium timescales, releasing energy that eventually radiates away into the cold vacuum of space. This process is irreversible. Once hydrogen has been fused into heavier elements, it cannot spontaneously return to its original state. The nuclear fuel that powers stars represents a finite resource that, once consumed, cannot be replenished through any known physical process. On cosmic scales, the expansion of the universe itself is a massive entropy-increasing process. As space expands, energy becomes more diluted and temperatures drop. The cosmic microwave background, which began as intensely hot radiation in the early universe, has been stretched and cooled by expansion to a current temperature of just 2.7 Kelvin above absolute zero. This cooling will continue indefinitely as expansion proceeds, eventually reducing all electromagnetic radiation to infinitesimally low energy. The formation and evolution of black holes represent another major contribution to cosmic entropy increase. When matter falls into a black hole, it disappears from the observable universe, but the black hole's entropy increases in proportion to the area of its event horizon. Stephen Hawking's discovery that black holes have entropy, and that this entropy is enormous compared to ordinary matter, revealed that black holes are among the most significant contributors to cosmic entropy. Even more remarkably, Hawking showed that black holes aren't perfectly black, but instead emit radiation due to quantum effects near their event horizons. This Hawking radiation represents the ultimate entropy-increasing process. Black holes slowly evaporate, converting their organized mass into random thermal radiation that spreads throughout the universe. The larger the black hole, the slower this process, but it is absolutely inevitable for all black holes. The entropy increase associated with cosmic expansion and black hole evaporation operates on timescales that dwarf ordinary stellar evolution. While stars exhaust their nuclear fuel in millions to trillions of years, the evaporation of stellar mass black holes takes on the order of 10 circumflex 67 years. Supermassive black holes, like those at the centers of galaxies, will persist for 10 circumflex 100 years or longer before finally evaporating completely. These enormous timescales reveal something profound about the universe's approach to heat death. The process is so gradual that countless generations of complex processes can occur during the transition. Entire ecosystems of stellar evolution, planetary formation, and potentially biological evolution can unfold during periods that represent tiny fractions of the time required for significant entropy increase on cosmic scales. But the mathematical inevitability of increasing entropy means that all of these complex processes are temporary fluctuations in the universe's overall slide toward equilibrium. Stars will exhaust their fuel. Planets will cool to match the temperature of space, and black holes will evaporate into radiation. No known physical process can reverse this trend or create new sources of usable energy once existing sources are exhausted. The concept of cosmic heat death raises profound questions about the meaning and purpose of organized complexity in the universe. If everything is ultimately destined to reach thermodynamic equilibrium, what significance do the intricate structures and processes we observe today have in the grand scheme of cosmic evolution? This question has puzzled physicists and philosophers since the thermodynamic evidence was first proposed. One perspective is that the temporary nature of complexity makes it more precious, not less. The fact that stars, planets, and potentially life exist at all represents a remarkable departure from equilibrium that can only occur during specific phases of cosmic evolution. We exist during one of the universe's most interesting and complex periods, when energy gradients are large enough to drive the formation of organized structures, but not so extreme as to prevent their stability. Another consideration is that our current understanding of physics may be incomplete. Just as quantum mechanics revealed phenomena that classical physics couldn't predict, future discoveries might reveal new physical processes that could alter the universe's trajectory toward heat death. Some speculative theories suggest that quantum fluctuations could occasionally reverse entropy increases on local scales, creating temporary islands of decreasing entropy in the overall sea of increasing disorder. However, such speculations remain highly uncertain, and all current evidence suggests that entropy increase is indeed universal and irreversible. The second law of thermodynamics has been tested more thoroughly than perhaps any other principle in physics, and no violations have ever been observed under controlled conditions. Understanding entropy's role in cosmic evolution is crucial for predicting where everything in the universe is ultimately going. The heat death scenario represents the most likely long-term outcome based on our current understanding of physics. A future in which all energy has been spread uniformly throughout space, all matter has decayed or been absorbed into black holes, and all black holes have evaporated into thermal radiation. This endpoint, while unimaginably distant in time, appears to be the inevitable destination toward which all cosmic evolution is heading. Neptune's orbit, as the universe continues to expand and evolve toward its ultimate fate, all matter and energy are being inexorably driven toward a single final temperature, absolute zero. This isn't just a theoretical prediction. It's a direct consequence of the fundamental physics governing cosmic expansion and thermodynamic equilibrium. Understanding this approach to absolute zero reveals the endpoint of cosmic evolution and the final state of all matter and energy in the universe. The temperature of empty space itself is already remarkably close to absolute zero. The cosmic microwave background, the afterglow of the Big Bang, currently has a temperature of 2.725 Kelvin, just barely above the point where all molecular motion would cease. This temperature has been steadily decreasing as cosmic expansion stretches the wavelengths of this primordial radiation, cooling it from the thousands of degrees it possessed in the early universe to its current frigid state. As expansion continues, this cosmic background temperature will continue to drop, following a precise mathematical relationship with the size of the universe. If the universe doubles in size, the background temperature is cut in half. This cooling will continue indefinitely, as long as expansion proceeds, asymptotically approaching absolute zero, but never quite reaching it. In a trillion years, the cosmic microwave background will have cooled to less than 0.003 Kelvin. In a trillion years, it will be immeasurably close to absolute zero. But the cosmic microwave background is just one component of the universe's thermal evolution. All forms of electromagnetic radiation, from gamma rays produced by the most violent cosmic events to radio waves generated by astronomical phenomena, are subject to the same cosmological redshifting. High-energy photons are gradually stretched to lower and lower energies, eventually becoming long-wavelength radio waves and finally disappearing into the infrared background of space. This process effectively removes usable energy from the universe's inventory. High-energy photons can drive chemical reactions, power photoelectric effects, and provide the energy needed for complex processes. But as these photons are redshifted to longer and longer wavelengths, they become increasingly useless for driving organized activity. Eventually, all electromagnetic radiation will be shifted to such low energies that it becomes indistinguishable from thermal noise. The approach to absolute zero affects not just radiation, but matter as well. All objects in space are constantly radiating thermal energy in the form of infrared photons. As long as an object's temperature exceeds that of the cosmic background, it will continue to lose energy through this thermal radiation. Brown dwarfs, cooling white dwarf stars, rocky planets, and even individual atoms floating in space will gradually radiate away their thermal energy until they reach equilibrium with the cosmic background. This thermal equilibration operates on different timescales for different objects. Small objects cool relatively quickly. A rocky planet ejected into interstellar space will cool to match the cosmic background temperature within millions of years. Whole, larger objects take much longer due to their greater thermal mass. Whole white dwarf stars, despite having surface temperatures of thousands of degrees, will require trillions of years to cool to match the cosmic background. Whole, the most massive white dwarfs might not complete their cooling until the cosmic background itself has dropped to nearly absolute zero. The approach to absolute zero has profound implications for the survival of organized complexity. Most chemical reactions require activation energy that become increasingly difficult to achieve as temperatures drop. At very low temperatures, even the simplest chemical processes cease, and matter becomes locked in its lowest energy states. Complex molecules break apart, crystalline structures become rigid and unchanging, and all forms of organized activity grind to a halt. Near absolute zero, quantum mechanical effects become dominant in determining the behavior of matter. Individual atoms and molecules settle into their quantum ground states, the lowest possible energy configurations allowed by quantum mechanics. In this regime, the classical physics that governs most familiar processes gives way to quantum behavior that is largely static and unchanging. However, even at temperatures approaching absolute zero, quantum mechanics predicts that some activity will continue. Quantum fluctuations, spontaneous, temporary violations of energy conservation allowed by Heisenberg's uncertainty principle will continue to occur, even at absolute zero. These fluctuations are incredibly tiny and brief, but they represent the only form of activity that can persist in a universe that has reached maximum entropy. The timeline for the universe's approach to absolute zero depends on the continued expansion of space. If cosmic expansion continues indefinitely, driven by dark energy or some other mechanism, then the cooling will also continue indefinitely. The universe will asymptotically approach absolute zero over timescales that dwarf even the longest stellar lifetimes. Horizons that dwarf even the longest stellar lifetimes. But there are scenarios where this cooling might be interrupted or reversed. If the expansion of the universe somehow slowed or reversed, the cosmic background temperature could begin to increase again. Some speculative theories suggest that quantum effects might occasionally create localized regions where temperatures temporarily rise above the cosmic background, providing brief opportunities for complex processes to resume. The approach to absolute zero represents more than just a temperature change. It signifies the end of all thermal gradients. On January 1st, temperature differences are what drive heat engines, power atmospheric circulation, and enable energy to flow from hot objects to cold ones. When everything reaches the same temperature, these processes cease, and the universe enters a state of perfect thermal equilibrium where no work can be extracted from the available energy. Understanding this thermal evolution is crucial for predicting the ultimate fate of all organized structures in the universe, from galaxies and stars down to individual atoms and subatomic particles. In the unimaginably distant future, when the last red dwarf stars have exhausted their nuclear fuel and cooled to invisibility, when brown dwarfs have radiated away their thermal energy, and when even the most massive white dwarf stars have cooled to match the temperature of space, black holes will emerge as the universe's final gravitational monuments, the last organized structures in a cosmos approaching maximum entropy. These cosmic remnants represent the ultimate victory of gravity over all other forces, while electromagnetic forces hold atoms together and nuclear forces bind protons and neutrons in atomic nuclei. Only gravity has the reach and persistence to create structures that can survive the universe's approach to heat death. Black holes are gravity's most extreme expression, regions where space-time curvature becomes so intense that not even light can escape. The black holes that will dominate the far future come in several varieties, each with vastly different lifespans. Holes in mass black holes, formed from the collapsed cores of massive stars, typically contain between 3 and 20 times the mass of our Sun, compressed into regions smaller than cities. These objects will persist for approximately 10 circumflex, 67 years before completely evaporating through Hawking radiation, a timescale so vast that it dwarfs the current age of the universe by more than 50 orders of magnitude. Intermediate mass black holes, if they exist in significant numbers, contain hundreds to thousands of solar masses and will survive even longer. But the true monarchs of the far future will be the supermassive black holes that currently lurk at the centers of galaxies. These giants, containing millions to billions of solar masses, will persist for 10 circumflex 100 years or more, outlasting everything else in the observable universe by unimaginable margins. During their reign as the universe's dominant structures, black holes will continue to grow by accreting any matter that ventures too close to their event horizons. In the sparse environment of the far future, this accretion will be minimal, perhaps an occasional rogue planet, a wandering brown dwarf, or debris from long-dead stellar systems. But even these rare meals will add to the black hole's mass and extend their already incredible lifespans. The physics of black hole evaporation, first described by Stephen Hawking in the 1970s, reveals that these objects are not truly eternal. Quantum effects near the event horizon cause black holes to emit radiation with a temperature inversely proportional to their mass. Paradoxically, this means that smaller black holes are hotter and evaporate faster than larger ones. The smallest possible black holes, if they exist, would evaporate almost instantaneously, while the most massive supermassive black holes will barely emit any Hawking radiation at all during the current epoch. As black holes evaporate, they slowly convert their organized mass into random thermal radiation that spreads throughout the universe. This process represents the universe's most prolonged entropy-increasing mechanism. The radiation emitted by evaporating black holes carries no information about the original matter that formed them, creating what physicists call the information paradox, the apparent loss of quantum information that challenges our understanding of physical law. The final stages of black hole evaporation are predicted to be spectacular on quantum scales. As a black hole shrinks to microscopic sizes, its Hawking temperature increases dramatically, causing it to emit increasingly energetic radiation. The very last moments of a black hole's existence involve the explosive release of its remaining mass energy in a burst of high-energy particles and radiation. But even these final explosions will be rare events in the far future universe. The evaporation process is so slow that black holes formed today will outlast the proton decay process. If it occurs, the cooling of all normal matter to absolute zero, and the expansion of the universe to sizes that make today's cosmos seem microscopic, providing direct evidence. During the long black hole era, these objects will be essentially the only sources of energy in the universe. The feeble Hawking radiation they emit will represent the last trickle of usable energy available to drive any form of organized process. Some speculative theories suggest that advanced civilizations might attempt to harvest this energy, using black holes as ultra-long-term power sources for maintaining complexity in an otherwise dead universe. The era of black hole dominance represents a profound transition in cosmic evolution, from a universe filled with diverse structures and energy sources to one containing only the most gravitationally bound objects, slowly evaporating into the void. Understanding this era is crucial because it spans the longest period in cosmic history, lasting perhaps 10 circumflex, 100 years, while everything else fades away around these gravitational monuments to the early universe's violent past. In 1974, a young theoretical physicist named Stephen Hawking made a discovery that would fundamentally change our understanding of black holes and reveal the ultimate fate of the universe's most enduring structures. By applying quantum field theory to the curved space-time around black holes, Hawking showed that these seemingly eternal objects actually emit radiation and slowly evaporate, a process so gradual that it makes stellar evolution look like lightning by comparison. The physics behind Hawking radiation emerges from one of the most counterintuitive aspects of quantum mechanics: the uncertainty principle applied to energy and time. Even in perfectly empty space, quantum fluctuations constantly create pairs of virtual particles that briefly exist before annihilating each other. These fluctuations are normally unobservable because the particle pairs destroy each other almost immediately, returning the borrowed energy to the quantum vacuum. But near a black hole's event horizon, something remarkable happens to these quantum fluctuations. The intense gravitational field can separate virtual particle pairs before they annihilate, with one particle falling into the black hole while the other escapes to infinity. The escaping particle becomes real radiation, while the particle that falls in carries negative energy into the black hole, slightly reducing its mass. From an outside observer's perspective, the black hole appears to emit thermal radiation with a temperature inversely proportional to its mass. This inverse relationship between mass and temperature creates a fascinating paradox in black hole evolution. Smaller black holes are hotter and evaporate faster, while larger black holes are cooler and evaporate more slowly. A black hole with the mass of our Sun would have a Hawking temperature of about 60 billionths of a Kelvin, far colder than the current cosmic microwave background. Such a black hole would actually absorb more energy from the cosmic background than it emits through Hawking radiation, causing it to grow rather than shrink. Only when the cosmic background temperature drops below a black hole's Hawking temperature will the object begin to lose mass through evaporation. For solar mass black holes, this crossover point won't occur until the universe has expanded enough to cool the cosmic microwave background to less than 60 billionths of a Kelvin, a process that will take approximately 10 circumflex, 67 years. The timescales involved in black hole evaporation are almost incomprehensibly vast. A black hole with the mass of our Sun will take approximately 10 circumflex, 67 years to evaporate completely. To put this in perspective, this is longer than the current age of the universe by a factor of 10 circumflex, 57. If the entire current age of the universe were compressed into a single second, the evaporation of a solar mass black hole would still take 10 circumflex, 49 years. Supermassive black holes take even longer to evaporate. The black hole at the center of our galaxy, Sagittarius A*, contains about 4 million solar masses and will persist for roughly 10 circumflex, 93 years. The most massive black holes known, containing billions of solar masses, will survive for 10 circumflex, 100 years or longer. Its timescales are so vast that they approach the realm of pure mathematical abstraction, far beyond any meaningful physical intuition. During most of this evaporation process, black holes emit radiation at such a low rate that they appear essentially eternal on any observable timescale. A solar mass black hole currently emits roughly 10 circumflex 28 watts of power, less energy per second than a typical flashlight battery produces in 10 circumflex 20 years. This radiation is also spread across all wavelengths, with most of it in the form of extremely long wavelength radio waves that would be impossible to detect against the cosmic background. But the final stages of black hole evaporation tell a very different story. As a black hole loses mass, its Hawking temperature increases, causing it to radiate more and more energetically. When a black hole shrinks to about the mass of a mountain, 10 circumflex 15 kilograms, its temperature reaches billions of degrees, and it begins emitting significant amounts of gamma radiation. The final second of a black hole's existence releases as much energy as a billion hydrogen bombs. This runaway evaporation process means that the end comes suddenly after eons of gradual decline. For nearly all of its existence, a black hole barely radiates at all. Then, in its final moments, it releases most of its remaining mass energy in a brilliant flash of high-energy radiation. This final explosion represents the conversion of the black hole's organized mass into completely random thermal radiation, the ultimate victory of entropy over structure. The radiation produced by black hole evaporation carries another profound implication for physics. According to Hawking's original calculation, this radiation is completely thermal and random, containing no information about the matter that originally formed the black hole. This creates the black hole information paradox, the apparent destruction of quantum information that many physicists believe should be impossible according to the fundamental laws of quantum mechanics. Resolving this paradox has become one of the most important challenges in theoretical physics, with implications for our understanding of quantum gravity, the nature of spacetime, and the fundamental structure of reality. Some physicists argue that information is somehow encoded in subtle correlations in the Hawking radiation, while others propose that black holes don't completely evaporate, but leave behind tiny remnants that preserve the original information. Regardless of how the information paradox is resolved, the evaporation of black holes through Hawking radiation represents the final chapter in the universe's structural evolution. After all, stars have died, all planets have cooled, and all normal matter has decayed or been absorbed into black holes. The slow evaporation of these gravitational remnants will be the last significant process occurring in the cosmos. The universe that emerges from this final evaporation will be fundamentally different from anything we can observe today. Whole matter will have been converted to radiation, all structure will have been erased, and all information about the universe's rich history of stellar birth, planetary formation, and potentially biological evolution will have been scattered as random thermal photons across an unimaginably vast expanse of empty space. Understanding Hawking radiation and black hole evaporation is crucial for predicting the ultimate fate of all matter and energy in the universe. This process represents the final mechanism by which organized structure succumbs to entropy, completing the transformation from a universe filled with complexity and information to one containing only the most elementary forms of energy spread uniformly through space. After the last black hole has evaporated in a final burst of Hawking radiation, the universe will enter its ultimate phase, a vast cold expanse containing only the most basic constituents of matter and energy, diluted to unimaginable thinness by eons of cosmic expansion. This elementary particle universe represents the final endpoint of cosmic evolution, where complexity gives way to fundamental simplicity, and all the grand structures we observe today are reduced to their most basic components. The inventory of this far future universe will be remarkably sparse and simple. The dominant constituents will be photons, particles of light that carry no mass, and travel at the speed of light through empty space, empty space. These photons will be the descendants of all the electromagnetic radiation ever produced in the universe's history. Starlight, from the first generation of stars, the cosmic microwave background, stretched by expansion to infinitesimally long wavelengths, and the final bursts of Hawking radiation from evaporating black holes. By this epoch, cosmic expansion will have stretched these photons to wavelengths longer than the observable universe itself. What began as high-energy gamma rays from violent cosmic events will have been redshifted to radio waves with frequencies so low that their wavelengths span distances larger than galaxy clusters. These ultra-long wavelength photons will carry virtually no energy and will be indistinguishable from the quantum fluctuations of empty space. Alongside the photons will be other stable elementary particles, though in much smaller numbers. Electrons and positrons, if they haven't all annihilated with each other, will drift through space as isolated particles, their electric charges maintained, but their ability to participate in atomic structures long since eliminated by the vast distances separating them. Neutrinos, those ghostly particles that barely interact with matter, will continue their nearly straight-line journeys through space, carrying tiny amounts of energy from the universe's distant past. The particle density in this future universe will be incomprehensibly low. Today, space contains on average about 1 hydrogen atom per cubic meter. In the elementary particle universe, the density will be so low that individual particles might be separated by distance distances equivalent to the current size of the observable universe.
How do you represent an entire species?
To Lurvin, you say, the chances of any two particles ever encountering each other will be effectively zero, making all forms of interaction and organization impossible. This sparse distribution reflects the fundamental victory of cosmic expansion over all forms of attractive force. While gravity once gathered matter into stars and galaxies, and electromagnetic forces once bound electrons to nuclei to form atoms, the expansion of space has now overcome all these interactions. Particles exist in perfect isolation, unable to influence each other across the vast gulfs of empty space that separate them. The temperature of this elementary particle universe will be essentially absolute zero, with the cosmic microwave background having been stretched to wavelengths so long that it carries no measurable energy. Individual particles will have long since radiated away any thermal energy they once possessed, settling into their quantum ground states, the lowest possible energy configurations allowed by the laws of physics. In this frozen dilute state, time itself takes on a different character, with no complex structures to evolve, no energy gradients to drive change, and no interactions between particles. The universe enters a state where nothing meaningful happens. Particles drift through space, following perfectly straight trajectories, separated by distances so vast that they might as well exist in completely independent universes. Yet even in this seemingly static state, the universe retains some vestiges of its dynamic past. The particles themselves carry information about their origins. An electron formed in the core of a long-dead star retains its charge, and quantum properties unchanged. The photons, despite their infinitesimal energies, still propagate through space at the speed of light, carrying the last whispers of information from the universe's active past. The concept of causality becomes almost meaningless in this elementary particle universe, with particles separated by distances that light would take longer than the age of the universe to cross, and with the expansion of space making even light speed travel ineffective for bridging these gaps. No particle can influence any other. Each particle only exists in its own isolated light core, cut off from all external influence. This isolation raises profound questions about the nature of existence itself. In what sense do these particles exist if they can never interact with anything else? The universe has become a collection of completely independent quantum systems, each evolving according to its own internal dynamics, with no possibility of external influence or observation. The elementary particle universe represents the ultimate expression of the second law of thermodynamics applied to cosmology. All available energy has been distributed as uniformly as possible. All organized structures have been torn apart by expansion, and all information has been diluted beyond recovery. The rich tapestry of cosmic evolution, from the Big Bang through star formation, planetary development, and potentially biological evolution, has been reduced to its most fundamental components, scattered across an unimaginably vast and empty space. This state appears to be truly eternal, with no energy gradients to drive change, and no mechanisms for particles to find each other across the expanded space. The elementary particle universe could persist forever, a monument to the universe's journey from initial simplicity through complexity and back to final simplicity. Understanding this endpoint is crucial for grasping the ultimate fundamental cosmic evolution and our place within the grand narrative of existence. Even in the apparent death of the elementary particle universe, quantum mechanics suggests that the story may not be entirely over. In the deepest possible vacuum, at temperatures approaching absolute zero, with particles separated by distances that dwarf galactic superclusters, the quantum nature of reality ensures that some form of activity, however minimal, will continue forever. Quantum mechanics tells us that perfect stillness is impossible. Heisenberg's uncertainty principle demands that energy and time cannot both be precisely defined, which means that even empty space must experience constant fluctuations in its energy content. These quantum fluctuations are not just theoretical curiosities, they're fundamental features of reality that have been measured in laboratory experiments and whose effects can be observed in phenomena like the Casimir force between closely spaced metal plates.
He knew that
in the elementary
particle
particle universe, these quantum fluctuations take on a new significance. With no other processes occurring, no complex structures evolving, and no macroscopic changes happening, quantum fluctuations become the only source of novelty in the cosmos. Virtual particle pairs will continue to spontaneously appear and disappear throughout space, borrowing energy from the quantum vacuum for brief moments before returning it. The scale and frequency of these fluctuations will be extraordinarily small. In the cold, expanded universe of the far future, most quantum fluctuations will involve the creation of virtual photons with wavelengths comparable to the size of the observable universe. These fluctuations will be so gentle and brief that they would be undetectable by any conceivable measurement device, yet they represent the only form of action occurring in an otherwise perfectly static cosmos. But quantum mechanics allows for more dramatic possibilities, however rare they might be. Statistical mechanics predicts that given infinite time, even incredibly improbable events will eventually occur. In the elementary particle universe, this means that occasionally, perhaps once every 10 circumflex, 50 years or longer, quantum fluctuations might create temporary concentrations of particles that briefly recapitulate some of the organizational complexity of the universe's past. These fluctuations could, in principle, spontaneously create anything that doesn't violate conservation laws. Isolated atoms, simple molecules, or even larger structures like planets or stars. The probability of such events is unimaginably small, so small that they're essentially impossible during any finite period we could meaningfully consider. Yet, over the infinite expanse of time available in the elementary particle universe, even these impossibly rare events become inevitable. Some theoretical physicists have speculated about even more dramatic possibilities. If the universe is truly infinite in spatial extent, then quantum fluctuations occurring across vast regions of space might occasionally create bubble universes, regions where the local energy density spontaneously increases enough to trigger a new period of inflation and cosmic evolution. These bubbles would expand rapidly, creating new universes within the larger elementary particle cosmos. The mathematics of such processes push the boundaries of meaningful calculation. The timescales involved are so vast that they're expressed using exponential towers of exponents, numbers so large that they cannot be meaningfully compared to anything in our experience. A typical estimate for the spontaneous quantum creation of a single hydrogen atom might be 10 circumflex 26 years, while more complex structures would require timescales that dwarf even these incomprehensible numbers. These quantum processes also raise fascinating questions about the nature of identity and continuity across cosmic time. If quantum fluctuations can occasionally recreate complex structures, they might theoretically recreate exact copies of things that existed in the universe's distant past, perhaps even copies of planets, civilizations, or individual conscious beings. These quantum resurrections would have no causal connection to their originals, and would exist only briefly before dissolving back into the elementary particle background. The possibility of such quantum events provides a strange form of immortality to the information that once existed in our universe, while the organized structures that created and stored information have long since been destroyed. The quantum nature of reality ensures that this information might occasionally be recreated through purely random processes. Every book ever written, every thought ever thought, and every experience ever lived might theoretically reappear in some future quantum fluctuation. However, it's important to recognize that these quantum possibilities exist in a realm so removed from normal physical intuition that they're more philosophical than practical. The timescales involved are so vast that they're essentially infinite from any meaningful perspective, and the events themselves would be so brief and isolated that they couldn't maintain any continuity with the universe's past. Nevertheless, quantum fluctuations in the void represent the ultimate expression of possibility within physical law. The suggestion that even in the universe's final state, The fundamental creativity of quantum mechanics ensures that something, however minimal, will always be happening in the depths of space and time. As we contemplate the elementary particle universe, with its isolated particles drifting through vast, empty space, punctuated only by the occasional quantum fluctuation, a profound question emerges. Is this truly the final chapter in cosmic evolution, or might there be mechanisms, known or unknown, that could alter this seemingly inevitable trajectory toward maximum entropy and heat death? The scenario we've described, often called the heat death of the universe, is based on our current understanding of physics and cosmology. It assumes that dark energy continues to drive accelerating expansion indefinitely, that the standard model of particle physics is complete, and that no new physical phenomena emerge on the ultra-long timescales required for cosmic evolution to reach its apparent endpoint. But history teaches us to be humble about the completeness of our physical theories. Consider how many times revolutionary discoveries have overturned scientific orthodoxy. Newton's mechanics seemed complete until Einstein revealed its limitations with relativity. Classical thermodynamics appeared to describe all thermal phenomena until quantum mechanics revealed the statistical nature of entropy. Even today's standard model of particle physics, despite its remarkable success, is widely believed to be incomplete, lacking explanations for dark matter, dark energy, and the unification of gravity with quantum mechanics. One possibility that could alter the universe's fate is vacuum decay. Our current understanding suggests that the Higgs field, responsible for giving particles their masses, exists in a metastable state, rather than the absolute lowest energy configuration possible. If this is true, then there's a chance that the vacuum could spontaneously tunnel to a lower energy state, creating an expanding bubble of true vacuum that would fundamentally alter the laws of physics within it. Such a vacuum decay event would propagate at the speed of light, eventually encompassing the entire observable universe, and changing the fundamental constants that govern matter and energy. Depending on the nature of the true vacuum, this could either lead to the immediate destruction of all existing matter, or the creation of entirely new forms of physics that might support different types of complex structures. Another possibility is that our understanding of entropy and the second law of thermodynamics is incomplete. Some theoretical physicists have proposed that gravity might allow for violations of the traditional formulation of the second law on cosmic scales. The formation of black holes, for instance, represents a decrease in entropy of ordinary matter, even though the black holes themselves have enormous entropy. Perhaps there are gravitational processes we don't yet understand that could reverse entropy increase under certain extreme conditions. The phenomenon of cosmic inflation in the early universe provides another intriguing possibility. Inflation was driven by a scalar field that caused space to expand exponentially, creating our observable universe from a tiny quantum fluctuation. Some models suggest that inflation might be an eternal process, constantly creating new regions of space-time with different physical properties. If true, our universe's heat death might represent only a local minimum in an eternally created multiverse. Even within our current physical framework, there are scenarios that could lead to different cosmic endpoints. If dark energy is not truly constant, but instead varies over time, the universe's expansion could eventually slow down, or even reverse. A weakening of dark energy might allow gravity to stage a comeback, enabling new structure formation, even in the far future. Conversely, if dark energy grows stronger over time, it could lead to a Big Rip scenario where expansion accelerates so rapidly that it tears apart all bound structures, from galaxies down to atomic nuclei. The possibility of cyclic universes represents another escape from heat death. Some cosmological models propose that